Hi everybody, and welcome to a video on a general overview of the different computer operating systems. And from there, I'm going to be sort of focusing on Linux really, but I want to give you a good taste about like what the different operating systems are and how they kind of work into your environment. And from there, I'm going to really start to play with a virtual machine and show you how to set up something like an Ubuntu or Kali VM. And then from there, depending on how long this goes, if not, it'll be in a future video, I'm going to jump into showing you some basic terminal commands. So I know this is very ambitious to say I'm giving you an overview of computers, and I mean, there's full courses you can take and still be just a beginner at something like Windows or Linux. But I'm just trying to say, like, you know, this is sort of the big picture for those of you that just are brand new to computers in a way, okay? And that's kind of the focus of this video, really, is just kind of, for those that are really not familiar with, particularly with Linux, who maybe have used a computer for like Microsoft Office or things like that, which you might think you're expert computer just because you use Microsoft Office, but no. There's so much more than just being able to use a computer for emails and spreadsheets and writing papers, okay? So that's kind of the goal of the video here, okay? And we'll see where we get there. So let's go ahead and just start by talking about the different operating systems out there. So there's a lot of operating systems out there. I mean, North Korea has their own operating system, and Russia has their own operating systems, and a lot of countries have operating systems. But even those we could generalize into the three sort of main groups that are popular today. And those are going to be your Apple's Macintosh, Mac OS operating systems, and sort of their derivatives. And then on the other hand, we have Windows, and that's pretty much Windows 10, 11, and so on, and Linux. Now, why do I say derivatives, particularly for Mac OS? Because then you also have things like on the mobile world, right? So you have things like Android, and Android is kind of Linux-based in a way. And the iPad iOS is kind of based on Mac. And so there's certain sort of derivatives of that, but they're kind of different. So really what I'm focusing right now is just the home desktop user operating systems, okay? So not necessarily mobiles. I mean, there's a mobile version of Windows that works on phones. And I'm not 100% sure on the if that's like Android based or if it's really like Windows based, but yeah, so I mean, this goes beyond that. And there's also a lot of specific operating systems for like embedded hardware and things like that, like what your car runs. Your car's not running on Windows or Mac. It might be running on Linux, actually. I don't think so. But there's probably certain, operating systems for those kinds of specific usages. So again, we're focusing just on the desktop user. Now, what do I mean by desktop? I guess maybe I should go that level. I am talking about a home computer meant for a human to use with an interaction in terms of keyboard and mouse. Or better yet, a good way of describing what a desktop computer would be is to talk about the von Neumann architecture. So let's start with that. So, and of course, some of you may be familiar with some of these concepts, and for those of you, you can just fast forward or you can just skip this video entirely. Again, this is really like for those that are just starting from scratch in a way. Okay, so you can go and read a Wikipedia on who von Neumann is. Again, a lot of the topics I'm talking today could be like full semester-long courses. In fact, in the CS program at UNLV, we have CS 219, which is called System Architecture, I believe, or Operating System Architecture. And so that class deals just with architectures in general. And so, I mean, like, we are making broad generalizations to just kind of move along. But it's still important to talk about von Neumann's because it starts to give you a picture of what is a computer, what makes a computer, right? And so you can kind of divide it, at least on the first level, into three principal components for a computer, okay? And so we have some sort of processing unit, And we're going to split this further. So we're going to start with like the most basic. So this is some sort of processing. This is what I would consider the computer. So let's just actually label computer first. And that computer needs to have some information going into it and some information coming out of it. And so we want to call the information going into it the input, and then this information coming out the output. And obviously there's some magic going on to transform that input into an output, right? So think of it this way. You ask a question to the computer, like what is 2 plus 2? And so your input is 2 plus 2. And then the output is hopefully going to be 4, right? So that is some computation that is happening there. Now, what is that magic or computation that is happening? Well, that involves splitting the computer aspect into multiple components. And the two major components that you can think of are what is known as the CPU and memory. Okay, so this computer is basically going to have a CPU component and a memory component. Now, these two could be combined. Again, when you're looking at things like an embedded device in a car or something, it's only in one big chip, like a PCB chip. And so, in fact, look around to see if I have a PCB chip. I have a Raspberry Pi, but that takes so much effort. But here, let me just very quickly pull up a picture of a PCB so you can see what I'm talking about. Printed circuit board, by the way, that's what PCB stands for. And here's just an example of one from Wikipedia's printed circuit board article. Okay, so this is a PCB. And so actually, I'll refer back to that picture in a minute. But yeah, so when you're thinking of a computer, you're thinking of these components, a memory component and a CPU, which stands for Central Processing Unit. It's kind of important to spell that out. Now, why do you need this CPU and this memory? Well, the central processing unit, again, is what's actually doing the computations, right? So it needs to know like how to actually do 2 plus 2. But more than that, for it to be able to do that, it needs to store somewhere the input it's receiving, so the 2 plus 2, and then it needs to temporarily store somewhere the output before it sends it out there. And why would you need to store it? Well, let's say you ask it to do like 2 plus 2 plus 2. And maybe the computer can only first do the first 2 plus 2, store that output, and then add the plus 2 after that because you're doing 2 plus 2 plus 2. And so it would need to have some sort of, memory to do like to save like your work as you're processing, right? So I guess a more realistic example is imagine I give you a bunch of computations to do, like 20 of them. And so and it's something where you have to add the result of all of them together into one big number. Well, you need to have some sort of scratch paper so you can keep track of what your like in between process like result is, right? So you can think of that as what the memory is doing. It's being able to store any information it needs when it receives it from the user, and also to store any work in progress until it finally gets the final result, and then they can spit that out into your output. Okay, so the memory chip and the CPU chip are usually separate in something like a home computer, but they can be combined for certain devices. But even in the times that they are combined, if you look at an actual PCB like this, they might actually look separate. Now, there's a lot of different types of memory. There's things known as registries. This little tiny memory that is super fast and it's really close to where the CPU is. And so that memory is probably going to be in the same chip. But if you're just having like big chunks of memory, that's usually on its own chip. So like this could be the actual CPU. And then, these codes actually mean different things, but maybe this is the RAM one. Okay, I'm just guessing right here. And then you see all these little lines here. They're actually the connections. They're organized in a way so that it's all in like a flat little board versus like a bunch of wires all over the place. If you ever take like a computer engineering laboratory course like CP 100 at UNLV, you would actually be using a breadboard, and you would be connecting these chips with actual little wires that would go into the breadboard. And it's a pretty cool thing. Again, maybe I can pull up a picture of a breadboard so you can see what I am talking about. I actually have one of these somewhere in my garage. Yes. So I just thought I'd share that. So this is a PCB. Now, that's not a very exciting picture because there's nothing plugged into it. So maybe I can find another picture of a PCB with wires in it or something. So you can see what one looks like. Oh gosh. Well, this is one extreme. I'll show you that picture too. But let me just show you more of a, well, that one's kind of nasty too. They're really going from like nope wires to too many wires. There are really no simple PCB board images that I can pull up. Well, yeah, I guess this one's kind of decent. Okay, so this isn't particularly what I was hoping to find, but it is what we have, you know. Okay, so I guess I'll show you this one. So, I mean, this is not a PCB board. This is actually looks like the upside down of an actual not a breadboard, but like just a PCB. But you can see the wires connector going from like here to here. These are actually soldered in. Solder means like it's a metal you melt, and so it allows the metallic connections to basically stick, per se. It's the overgeneralization of soldering. This looks like it might have been a PCB board at some point, but it's been just riddled with wires. But yeah, so basically the idea is that you have the board and that you can and that you can connect the board and the little chips that you get, so you can make them communicate. Okay, so anyways, that's all I'll say about that. I don't want to scare you with all these weird pictures of wires. Yeah, I wish I had a nicer picture of a PCB, but yeah, okay. So anyways, going back to the von Neumann, that's the idea, that you have these two things that are communicated, and then on the outside you have the input and the output, right? And so the CPU can further be broken down into two sort of important components, and those are going to be your control unit and your ALU, which stands for arithmetic logic unit. And so what that means is the control unit is what basically controls like what the steps are, what is next, what's before, and so on. It controls the general flow of a program. And then the arithmetic logic unit is actually like the worker. That's the person that's actually doing the math. And as the term arithmetic hints you, that's what they're doing. So really, a computer is nothing more. And I'm talking like even your like super advanced computer you're watching this video on is nothing more than a simple calculator. It's just doing math. And guess what? Even that math can be simplified down into Boolean algebra. Now the word algebra sometimes scares people, but no, in this case it's like simple stuff. We're talking about logic, like and, or, and not. So that is literally all your computer can do. And everything that you have now, when you're playing Fortnite, or you're doing your spreadsheets, or you're watching a movie, or listening to a music on YouTube or something, that is all boiled down to a bunch of and, or, and not logic gates. So those are called logic gates. And so how do we make art from logic gates? Well, we just combine them in very creative ways. Again, I'd have to spend a couple of hours just teaching basic Boolean algebra for you to understand how to make even a simple add or subtraction calculator using just these three logic gates. It's not the point of this video. You can go out there and look at how that's done, okay? But just know that that's really what your computer is made of, which is pretty neat. So going back to sort of the big overview, now that we know that these are all the components, what it ends up looking like in your modern computer is like follows. You have your CPU tower. If this is a desktop machine, back in the day they used to have CD drives, but now they don't. So they're just kind of just a box, I guess. Now it's kind of sad. But yeah, so you got like a num button here or something, and then this is plugged in to an I/O device. So I/O is a abbreviation for input output, and like I said, just the von Neumann says there's input devices and there's output devices and there's the CPU, and now we know that CPU is made up of two components, which is memory and the CPU itself, and that CPU is made up of two pieces, which are the control and the ALU. Right? See? Now you know all the subdivisions. And you could try to divide it further, but the smallest you're going to get is going to be these logic gates, okay? The AND or NOR and NOT. Those are made out of silicon, and that's why Silicon Valley is the nickname, right? Well, actually, they're not made in Silicon Valley nowadays, but that's just where that comes from. That all of these things are made this tiny because of silicon, although we reached the point where we can't make it smaller, so that's kind of another whole story. We have Moore's law and all that stuff. Okay, but yeah, so your computer is plugged into certain input and output devices. An example of an output device that we all typically use, and you're using this exact moment, like right now, you're using it, you're even staring at it, is going to be your monitor. I guess I put a widescreen monitor, although I'm not a big fan of the widescreen ones. So this is an example of an output device that we all tend to have. Now, before I give you any other input or output devices, just think to yourself, which output device you're also using to get my voice? Well, that is in the form of a speaker, right? Or it could be a headset too. So it could be a headset or a speaker, which you can't see one, but I have some speakers around. Okay, so yeah, let's just say that here you have both. So as most people do, so maybe you have like, there's some really old school computers that that have these like hanging speakers on the side of the monitors. That's cool, but super old school. Actually, a lot of computers have the speakers just kind of built into the monitor sometimes. I never use them though. I like headsets or just like outside speakers. But yeah, so there could also be an audio jack here, which is like a 3.5 millimeter audio jack, and that goes in to some headphones, right? So these are all output devices. They're outputting different things, such as visuals or audio, but they're ultimately output devices because they're giving you information from the CPU. Sure, you're not getting math back, but you're still getting something that has been the result of these math computations. So you're getting music, or you're getting these RGB lights that are lighting up in a predefined sequence that is configured to make it look like a face of me speaking to you, right? So I guess RGB, if you don't know what that stands for, is just the colors. So your monitor itself works by having all these little LEDs. Well, modern ones. Back then you had like CRT TV and stuff. But modern ones, you can think of all of these having these little bulbs. And these bulbs are actually 3 bulbs in one. And those 3 bulbs are in 3 different colors: red, green, and blue. The idea is that if you combine them with the right number of, the right amount of light that is coming out of them, you're able to create any color on the rainbow. And so that is how RGB is done, basically. That's how you get colors and whatnot. So like, don't ask me to get you a color wheel, but I'll get to you anyways. RGB color wheel. This one's good. If I can get it at least to be full screen, that is. There we go. So here's an RGB color wheel. So you can see here that if you want to get red out of your RGB, you make the, so the ranges, I guess it's important. The ranges of how intense a red can be go from 0 to 255. There's a reason for that number. I'll come back to that after I finish this. So this red means that we are maxing out the red, and the green and blue are zeroed out. Well, that's because we get like pure red. Similarly, if we only wanted green, we'd only max out the green LEDs and then turn off the red and blue. And with blue, we turn off the red and green. But if we want to get something like yellow, what do? Well, yellow, as you see here, is at 60 degrees from the beginning of your wheel. You actually need to max out the red and the green. So if you throw red and you throw green at max, you turn both on, then because they're so close together, it looks like yellow to your eyes because both colors kind of mix there. And you keep the blue one off. Now, what happens if you turn them all on? Then you would get white. They all mix together and they create white. What if you want black? then you just turn them all off, and then you have off light, which hopefully looks black. That's why monitors had to struggle sometimes with actual proper black, because there's always some sort of residual backlight going on in there. Then you have things like OLED, which are better now. But yeah, that's basically how you get colors in your monitor. And then these are so tiny that you can basically color each one individually to how an image looks, and you get something like this. When you think about an HD image that is a 1080p, that means that there's 1080 of these pixels. So that's the name that we call each of these RGB LEDs. All three of them make 1 pixel. And so you have 1080 of those in a row horizontally to basically create your 1080p. There are also things like 4K and 8K. And so let me see if I can put them all side by side so you can kind of see the amount. Oh, that's a tiny picture. I like this one better because it has, yeah, okay. So look at this one. So this one shows you the actual number of pixels. So as you can see, for something like 1080p, I said horizontally earlier, I meant vertical. So for 1080p, it's actually 1080 rows, and each of those rows contains 1120 horizontally of these pixels. That technically means that you would have to multiply something like the 1120 times 3 to get the number of individual LEDs, because again, each LED has the 3 colors, red, green, and blue. And that's how many of those little light bulbs are in your monitor, basically. So take 1120 times 1080, that's the number of pixels you have total. And then multiply that times 3 to see these individual red, green, and blues that you have. You have, so here we can do the math really quickly. So if we do 1120 times 1080, we are getting approximately, well, not approximately, exactly 2 million. So 1920 times 1080, you get 2,073,600. Those are the number of pixels that you have. Each of those pixels is going to contain 1 red, 1 green, and 1 blue light. So if you LED. So if you wanted to know, you'd have to multiply it times 3. So then you'd get basically 6 million approximately. Okay. So going back to that picture though, you can see the difference between that and something like 4K, where you have 3,000. Essentially, you have. Well, you have about 4 times, kind of, but really you have 3,840 pixels, and then you have 2,000 rows of that. And so in 8K, you can see the difference. So yeah, I think this is actually to scale too. Standard definition, that was like, I think 420 or 480. You can see it on YouTube if you look at a standard definition video, like this video, maybe you can actually see, and it'll tell you the number followed by a P. So anyways, that's how monitors are run. And so when you're thinking about output, you know, it's a lot of output that's flowing to be able to fill this. And so for things like that, we have like HDMI or DisplayPort. And back in the day, we had like more analog versions like VGA and things like that. Okay, but anyways, going back to this, let's look at other outputs that we might have. Well, we like I said, these are kind of gone nowadays, but we also had a way to write data into storage. And so that storage was in the form of like a CD drive, a floppy drive, a USB stick, and so on, right? But those are all kind of gone now. Well, except for USBs, those are still here, or SD cards, right? And so those are technically I/O devices because they can send information outside of here, right? Another sort of category is the input devices. So you have a couple of input devices, typically with a computer, and the most popular one, well, there's 2 most popular ones, are going to be, what do you think that is? It's a keyboard, or at least I hope you thought it was a keyboard, right? So a keyboard is an example of an input device because you are entering information to the computer. The other very famous device is going to be your mouse. right? So your mouse is an example of another input device. And I would say that these two are the most important input devices that you can have. But you could also have inputs via things like the CD drive. You put in a music CD or a music floppy or a music USB or some photos from an SD card that you want to display in your computer. So in that case, it has to take in the data, process it, and display it to your output device, aka your monitor, right? You could also have one important one that I'm using right now also, and that is going to be your microphone, right? So that one is going to be also an input device because you're speaking into it and it is digitalizing your voice for generations to see. So yeah, there's that. Finally, one more input device that I am actively using, so therefore I remember to tell you, is going to be a camera, webcam, right? That one has become popular in the recent years because of things like remote learning, right? Because you have to record it. But I mean, it's a very old device. It precedes computers in a way, because you think about how old cameras are, right? So yeah, but we now have the ability to directly take the information from a camera into a computer at real time. So yeah, those are really the input devices that I can think of. Of course, if you're playing a video game and you plug in like a controller, oh, sad, I thought I had a controller right now, then that is technically an input device, right? So a joystick or a flight simulator stick or throttle, those are all input devices. And could also be output devices too, because something like the rumble feedback of a controller or a joystick, that's output because it's coming from the computer to you. So you're not necessarily limited to a device being only input or output. It can be both. So that can be said too, okay? But that's really when I say a computer, is particularly a desktop, is going to be this. Now, all this stuff can still be contained within something like a mobile phone, which will contain both I/O devices, such as your speakers, your microphones, your camera, also your monitor. In fact, I would say all of these except for maybe the keyboard. Technically, there's no keyboard, but as an alternative, there is a touchscreen. Oh, by the way, you could also have a touchscreen here if your monitor was touchscreen, but that's more of like a laptop thing, right? And the laptop is really, in a lot of ways, very close to a desktop. Typically, the limitations are going to be in terms of space. So you don't have the luxury of having so much space to fit as many features. Or also, you have to miniaturize some things, and that usually increases the cost and limits what you can put in there, even if you had unlimited cost in the way. So there is that as well, okay? Now, an important thing when it comes to this device is memory. So memory, right? So we talked about memory as one of those important things in the von Neumanns. So let's talk about different kinds of memory or storage that you have. So in a computer, the main components that you will see related to memory is you have a motherboard. And in that motherboard, you have your CPU. And then you have here your slots for what is known as RAM, which stands for random access memory. Those RAM slots allow you to insert RAM, that random access memory, which is very fast, but it's volatile, meaning that when you turn off your computer, that information is lost. Now, lost with a little asterisk, because you can technically recover RAM after it has lost power for a little bit of time afterwards. If you want to know more about that, then you have to look at forensics, right? How to extract information from the RAM that has been turned off. And one of the typical things, I took a course, and well, I knew this before already, but they kind of re-emphasized it, is that you supercool the RAM so that you can sort of see the state of it, and you can extract some information out of it as long as it's within a short period of time. And so, yeah, check that out more if you're interested in that kind of stuff. But again, that's all I'll say about that. It's also how RAM works. There's intricacies of that as well. Again, I would love to tell you right now, but I will save it I have videos on the CS219 that talk about this stuff. You're more than welcome to check those out. But that's all I'll say about RAM, okay? So the other, because RAM is volatile, which means that when you turn it off, it goes away, we need to have some sort of persistent data storage, right? I mean, how annoying would it be that every time you turn the computer off, all the information you have is gone, and now you have to reload it every single time? Well, welcome to the 90s. That's how it used to be until, well, maybe more like 80s, but that's how it used to be. Until we got this amazing thing called hard drives. Or not that we had, because we already had them, but at least they became more accessible to the general public. That's a really weird hard drive. That's not what they look like, but okay. That's usually what they're represented as, but really they're more like a rectangle that has like a plate on top. In fact, instead of my art, how about we pull up a picture of the hard drive? Hard drive. By the way, I claim no property of any of these images. They're just from the internet, so I didn't create them. So just FYI, I'm trying to get all of them from like Wikipedia or open sources to avoid copyright issues. But please, this is an educational video, so no copyright violation intended for these images. This is what a hard drive looks like. There are many like it, but this one's mine. No, basically, this one's not mine, but it's a platter. And this is a ceramic or different materials, composites made disc that is spinning really fast. And in it is a lot of little precipices and here for that, let me just draw it. That platter has a lot of little ups and downs that are kind of generated due to a magnetic force that is applied to them. And they represent the information that is stored. I still got to go back to tell you how that information is stored, which I said I would explain why that 255 was there for the RGB. I'll come back to that at some point. But basically, you're storing it in bits. And so that information is stored there for a really, really long time. I don't want to say forever, because maybe the hard drives at some point after 500 years, they might degrade enough that they lose information. But we haven't really reached those limits yet, as far as I know. So they're pretty good for storing information, at least for your lifetime. So yeah, this is the solution to the issue with volatile RAM. We can use these secondary storage devices, such as a hard drive, to be able to store information beyond a computer's active runtime. And so before these days, what were other ways that we could store stuff? Well, there were things like floppy disks. Let me pull up an image of a floppy disk for you. So that's a hard drive. And there's two kind of floppy disks. There was the, oh, perfect. Here's a picture of, oh, 3 times actually. I only remember 2. So, and that one's in Russian. So it might have been like a Russian thing. I don't know. But these are, so this is the floppy drive that I know, and I have some of those still, is the one right here. So those floppies, if I recall, I think you could store like 3 megabytes of data, something like that. Well, there's two. There was the high density and the low density, which was a scam because you could like quote unquote hack them by breaking a tab or something. I don't know. It was a thing we used to do. I forgot already. But I don't claim to have lived the floppy era. I kind of got the tail end of that, but I had them because my dad had them, kind of thing. But yeah, so I also remember, and I think we might still have some of the bigger ones, the 525-inch ones. Those are they work the same way. So they're like little magnetic discs as well, and they spin, and that's how they store information. So they're kind of a similar technology to how the hard drives are, but like obviously not as dense, because a hard drive could store a lot more information than the floppy could. And then I don't know what that big one is. I just assume it's like, when you want to store more, then just make it bigger. So I guess that's how that one is. But I see it has like some Russian in it. So I don't know. Sledano the Bulgari. Okay, very cool. If anybody knows what that is, post it in the comments. But yeah, that is a way of storing information in addition to the hard drives. And so that was what was popular, because I guess it was cheaper. And also it allowed you to take things, because a hard drive is like, it's not really meant, especially the old ones, were not meant to be moved around a lot. You could actually mess them up. Nowadays they're cool to move around. Like laptops have no issues with that. They have a locking mechanism so the thing doesn't like wobble or spin and break, because they're very fragile in a way. Think about it. There's all these little tiny ups and downs, and like you could like smash that thing very easily. But like I said, now they're pretty resistant. But back in the day, you were discouraged from even moving a computer, particularly when it was on. I think when it was off, like there's actually a command you could run in Windows that you would park the disk. And you were recommended to run that command to park the disk before actually physically moving the computer, even when off, just to make sure that it was okay. So yeah, it wasn't the best of ideas to be moving around big hard drives to transfer information between people. And there was no real internet back then. So, or at least no accessible to people outside like the military. And so really like the only way to transfer information was these floppy drives. It was like the USB of that time, okay? Or the SD card of that time. I bet you when USBs and SD cards go away now, you'll be like, oh yeah, what is that? What does that even mean? But at least most of you will know that because you still use those today, right? So we have things like USBs, and we have things like SD cards, and even tinier SD cards, actually. Like that. Think about it. This thing, the amount of information this has is 32 gigabytes. That's how big hard drives were, and they cost a lot of money. And there wasn't even, okay, even before they were even that, like there wasn't even a hard drive that was this big that was accessible. And now this is like $10. Think about that. Even with inflation, $10. Yeah. So that is another thing about like computers and how we are doubling the amount of space and keeping the same cost, and it just keeps growing. 219 stuff. But yeah, so that's another storage system basically, and ultimately we have evolved from these floppy drives and whatnot, and the hard drives are still in use, but now what is becoming popular is solid state disks. And solid state disks are good because as the term implies, they're solid, and so they don't, there's no moving parts, and so that's a good thing because we don't particularly like things moving around because that involves things that are mechanic in nature and move tend to wear down over time. That's just the nature of friction and things like that. And so this not only is faster, but also I would say potentially more durable. Now, asterisk there because these things do wear down and eventually they stop working in a much faster time than a hard drive, but still they have a different kind of wear and tear associated to it. But yeah, this is what a solid state drive looks like. And this is an NVMe SSD. There's also like the old school SSDs that look more like this one. I intend to make no recommendation on this brand, but there's that. So yeah, so these things are working much faster than a normal hard drive. So hard drive, there's two real speeds. There's the I think it's like 5200 and or 5600 and the 7200. And that stands for the amount of rotations per minute that they can do. And so that limits you because like, think about the platter, right? So if your platter, so like if you're reading from a disk, right? And you have a needle that reads from the disk right here. And let's say there's information right here. It needs to spin this way so that it actually rotates. So like, you know, if I want to get to the X, I have to rotate the disk to there, right? And if your max rotation speed is going to be 7,200 rotations per minute, so you can do the math and figure out how long it takes for the disk to rotate, what the longest distance would be to access the data, which if it can rotate in both directions, then it would just be half a rotation. But typically, I believe the hard drives are just rotating in one direction. So that means that the worst case scenario is you just passed it, so you just keep going. Because think about it, if you're rotating this thing at like, 7,000 rotations per minute, that's fast. I mean, it's not too fast, but it is pretty fast. So like trying to just like break that and then rotate it the other way, you're gonna really wear down the disk if you just have like some like locking mechanism that just like some like emergency, like think about like car brake system, or you just like keep going and then just let it spin. So really, worst case scenario is if it just passed it and needs to go all the way around. So you can compute that using the circumference of the disk, multiply that, do math with the RPM. You can figure out exactly how long that takes. It's going to be in the millisecond range. And so, yeah, so that's slow when you think about computers. Milliseconds, you might be like, well, millisecond, that's like so fast. well, for you it's fast, but like if you got to do a bunch of these, the computer is slow. Like when I'm playing Fortnite or whatever, you know, I want to be able to like move my screen and not feel this lag. So it has to be fast, right? So even milliseconds can be pretty slow. So that's why we moved to solid state, because we don't need to worry about this waiting for this physical rotation to basically match. Okay. So anyways, I think that really wraps up what the computer is made up and all the components. So again, you might have known all of this already, but I really wanted to just go from the bare bones beginner level and build up to fancier stuff. Okay, so with that, we kind of can move on to talking about the different operating systems. So I'm closing my 1 billion pictures that I've opened. Actually, oh, well, one more thing that I want to talk about, and it's kind of important. So let's talk about the way that computers communicate. Okay, so let's talk about binary. Kind of important to know binary. I mean, it's not really fancy or complicated. You'll get it pretty quickly. Don't let people scare you away like, oh, I know binary. That doesn't really mean anything. It's like, okay, I can learn it in 5 seconds too, and you are just about to if you don't know it. Okay, so let's talk about our normal numerical system that we use in everyday life. So at least in my year 2022, we use decimals, right? So like when we count, I count to 10. Like I have 10 fingers, you know, I can count all 10 different numbers and I'm good to go. I can go 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. I got all those 10 numbers in there, right? And then it starts repeating, because the number 10 is made up of the 0 and the 1, right? That's what it's made up of, right? It's not really its own number. Like the only unique numbers we have are 0 through 9, those 10 numbers. That's it. In fact, let me write them for you in case that future generations use different digits for the representation of these numbers. Okay, so that's it. Those are all the 10 digits that we have. And when we go from there, any other number is made up of these digits. Like the number 10 is literally made up of the 0 and 1. So I take the 0 and 1 and I just put it in a specific order. And so I've made up a new digit. Let's say I want to do the digit 225, right? What is that made up of? Well, that's made up of a 2, another 2, and a 5. So you can see that every single number that you can think of is made up of these 10 digits, right? And we call that decimal, right? Well, do we call it decimal? I think there's another name for it, actually. Let me triple check. Technically the other term we use, yeah, so I wanted to remember, is yes, yeah, this one. Denary. I think it's with a Y. Okay. So we use this denary system because there's 10 different digits, right? And it works for us. I guess we just somehow got used to this to the point that it just makes sense. Like 10 makes sense, 100 makes sense, all these numbers make sense. If I tell you to add 25 plus 20, you can very quickly add that and say it's 45. If I tell you to subtract numbers, multiply them, like it all makes sense because you learn it in school and it just clicks, okay? Cool. However, when it came time to make computers and to be able to store numbers in computers, to be able to store computers, numbers in computers, we would have needed to have 10 different states, right? To be able to represent each of these digits. And that's not really practical when it comes to computers, because really, when it comes to electricity, which is what the computers are running on and what the logic gates are working with, there's only really two states. There is on and there's off, right? So there's current passing through or no current passing through. There is a true state or a false state. There's nothing else in between, right or wrong, left or right, true or false, right? Just two states. That's it. There's nothing. So how do we represent numbers in that scenario? Well, that's very easy. Instead of using 10 symbols, let's just use 2 symbols. Doesn't really matter which symbols we use, but since we're so used to using the symbols that are shown here, let's just pick the first 2. And that's what they did. They picked the first 2, 0 and 1. So when you hear the term binary, it has this part to it. Bi means 2, whereas den means 10. That's where the term binary comes from. It's a numbering system where you're only using 2 symbols instead of what you're used to known as 10. There's things like hexadecimal, right? Or the fancy name, I suppose. Well, no, let's just say hexadecimal. Hexadecimal. So you just sometimes hear like hex, but I'd rather just teach you the whole full term, hexadecimal. So with hexadecimal, actually, it goes beyond 10. You're actually using 16 different digits. And you're like, whoa, wait a second. So wait, what are the other digits? Well, you know, when they did them, sure, they reused the ones that we already used. So they got all of these. But when it came to like coming up with new digits, I guess it could have done some like hieroglyphics, like, I'm going to create digits right now. Like, blah, that's a digit. All right, and then like maybe like, wow, well, that looks like a 2. Yeah, that looks cool. Maybe I can do, well, there's nothing that forbids you from doing curves. Or maybe we can do like a upside down, like an upside down 9. Like a D looking shape. And you're like, oh, you know, I mean, you could do this. But then the D is like, well, D, we have letters. Why don't we just use letters, actually? That's a good point. Let's just use letters. And so they said, okay, let's use letters. So they ended up using letters. So they just said, like, we'll just do A, B, C, D, and E, right? And yeah, is that 16? Yeah, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, one more. And let's just throw an F in there as well. Okay? So yeah, that's how hexadecimal was born. They decided to use the letters instead of using any weird unknown digit. Because, I mean, people know what the letters look like. They know how to draw them, or at least Westerners know how to draw them because they use them, right, in English and other those languages. So yeah, when you talk about hexadecimal, they're just using the letters for the extra digits. But you're like, whoa, what does that mean? Like, so wait, what is 10? 10's like an A? And yes, you can think of like 10 in the form of like what follows 9 being an A instead of being a combination of previous digits. And that's the important thing that you have to kind of understand. When you're using a number of, whatever base numbers you're using, whether it be binary, decimal or hexadecimal, you only have X number of digits available for your use. When you run out of them, then you combine the digits to create the next number in that sequence. So whereas with decimal, we combine the 1 and the 0 to make a 10, and then the next number is 11, which is just taking what we just made plus the next one and so on. That's the same thing you would do with something like hexadecimal. So from here, you get all the way to 15. And when you make 16, you just start by taking the first 2. So this is actually 16 in hexadecimal. Whereas in normal decimal, it represents 10 because we're combining the first 2 digits after we run out of digits. In hexadecimal, it actually represents 16 because the A is a 10. What about binary then? With binary, if you only have 2 digits, we run out of them pretty quickly. So how do I represent 2 in binary? Well, it turns out just like the 10. You combine the 2 digits together. Okay, so what follows after this? Well, you already combined the 2 digits, so then we can combine them in a different way in the one that follows, so we can put 2 of the second digit together, right? So we can make 11 be the next thing. And this actually represents 3 in binary. And what about then? Well, we already ran out of different ways of combining 2 digits. So we have to throw in a third digit to combine them. So we can do 1 of the 0, 0. So we take the second digit, and then we take the first digit twice. So this becomes a 4. And I hope you start to see the pattern here. If not, let's just do the hexadecimal version of this. Or actually, no, let's just do the decimal one. So think about it. When we have 2 digits here in decimal, so 10, we can combine the two digits, using this first digit here, we can combine them with all the other digits to make the numbers 11 to 19, right? But after that, we run out of digits. We have to change this first digit to something else to make new numbers. So that's why we raise it from 1 to 2. So now we can combine this with the other digits available from 0 all the way to 9 until we run out of the ones that start with 2. And then we do with 3. Eventually, when we get to the 90s, you know, we can combine it with anywhere from 90 to 99. But after that, once we've gone all the way to 99, we have no other combination left that can be used with sticking with just two digits. Because we always want to do the least amount of digits possible to save space per se. And so because we have run out of that, then we reset back to saying, well, okay, now we're going to do something with 3 digits. And so that's how we get 100. So that same logic is the same logic that is used for any base of numbers, including binary or hexadecimal. So that's why with binary, you run out quicker of the 2 digits. So you go to 3 digits very quickly. As you can see, when you reach 4, you already have 4 digits. Whereas here, you have to get to 100 to get to 3 digits. And with hexadecimal, it will take much longer because you have that. You have the ability to have 16. So like, you know, from here, I could go all the way to 1F before I have to go to 2,0. And then I could go all the way to 2F before I go to 3,0. And I would have to go all the way to 9F before I actually reach 100. How many numbers would there be there? I'll leave that to you as an exercise to figure out. And if not, then you can Google like hexadecimal converter and you'll find out. But remember, each time you have to go through 16 of them and you have to go through 10 of those. Actually, oh, no. Actually, I made a mistake here. From here, from 9F, you actually have letters now. So you can do like A0, right? Yeah, and then this can go all the way to AF. And then you can go to B0, which goes 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And then it goes to C. So only after we get to FF, then we can actually get to 100. Okay? So that's kind of important. So, yeah. Okay, almost made a mistake there. But now after that, you can figure out what is that equal to, and if it was in decimal. Okay, try to do the math for that, and then if not, then just Google it. Okay? So let me backtrack a little bit. Why are we using the binary? Well, like I told you, we have the on and off state. We do have the disadvantage, though, that your numbers can become very big very quickly. So like trying to represent the number 100 in binary is going to be a lot of digits. Here's a quick trick for figuring out how many digits. You can use exponents for that. So because there's only 2 digits that you have, you use 2 as the base. And so if you want to know how many digits you can store with just one digit, you make that power of 1. So 2 to the power of 1 is just 2, right? And that's true because you can, if you only have one spot, you can have a 0, you can have a 1. That's it. So you can only store 2 numbers. But what if you have 3 bits? Well, you can do 2 to the 3rd power. What's 2 to the 3rd? That's 8. That means that you can store 8 possible combinations. Is that true? Well, let's test it out. You'd have that. You'd have that. And that you run out of for that. So then you start using this one. That's it. So is that 8 of them? 1, 2, 3, 4, 5, 6, 7, 8. Yep, that is 8. And those would represent the numbers in decimal 0 to 7, right? Important thing that you should start to figure out, I always start counting from 0, and that's just a thing you do usually with programming as well. You always think of the first number of a sequence as 0, not as 1 as we typically tend to think in like normal math. Like what is if you start counting, if I tell you, hey, count to 10, you say 1, 2, 3, 4, 5, no. Computers, programmers, you say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Things like that. It's you just kind of get used to. Not to say that you don't ever use that, you never start counting from 1. Programs like programming languages like MATLAB start from 1. But the norm outside of the weird cases is you start from 0. That's what you typically learn to just get used to. Okay? So, but anyways, what would it be this in hex? Well, it would actually be the same here as these in hex, because you remember with hex you have more digits. So 0 to 7 would still be the same. So yeah, so this is a nice little rule to, or not rule, but trick to know how many digits you need to represent X amount of numbers. So now let's go back to thinking about the RGB. So the RGB has to store 0 to 255. Notice something about 255. If we see what is the range of these numbers, we see that there's actually 256 possible combinations because again, we're starting from 0. What's interesting about this number? Well, think about it. It's a power of 2, right? Let's see what the powers of 2s are. You go 2, 4, 8, 16, 32, 64, 128, 256. So yeah, so which one is that one? I don't know, what is it, like 2 to the 8 maybe, I think, or 2 to the 7? Let's see, what is 2 to the 8 is, yeah, 2 to the 8 is 256. So yeah, so that means that 2 to the 8 is equal to 256. It means that if we want to store 256 possible combinations, we need 8 bits. And that'll be able to store 0 to 255. So that is actually why the RGB values run from 0 to 255. So at first you might have been like, that's a really random number. But it's not. It's because we're able to communicate which exact tone of the red we're going to be running using 8 bits of information that represent the number from 0 to 255. So what does that look like? Well, you'd have 8 slots here. So 1, 2, 3, 4, 5, 6, 7, 8. And those will be combinations of zeros and ones. And so if you want to figure out what those are equal to in terms of decimal, so like what number that is, there's a lot of different formulas for doing this. You can use actually the fact that these are all powers to kind of extract information. So like, for example, you know that this is on the 7th position here. And because it's a 1, then it means that it should be like 2 to the 7th. So like it should be, this number is bigger than 128. So you can see something like 128, you know, plus this one's at the 6th one. So that's plus 64, plus 32, plus 8, plus 4. And then I think you might have to subtract 1 from this. But anyways, you could also just go online and look at decimal to binary converter. So this is from rapidtables.com. And so you can just go ahead and enter it. So let's use, we don't need to put the leading 0 in. 1110110. Convert. 118. Oh, I must have. Oh, I flipped these wrong. That's why. So 1101. Yep. So this is actually equal to 118. So actually, my exponents were off. So this is the 7th spot. 6, 5, 4, 3, 2, 1. Yeah. So I think. So really, if I were doing the math correctly, it would be 64 plus 32 plus 16. And then, so yeah, so this is the, so if this one was 1, it'd be 128. This is 64, this is 32, this is 16, this is 8, 4, 2, 1. And so we're adding 64 plus 32 plus 16 plus 4 plus 2. Is that equal to 118? Well, let's see. So this is 96 plus this is the other 4 there. So that's 102 plus 16. Yep, 118. Yep. So yeah, you could just use a converter, but that's one way to do it. So just make sure you start this at, if you have 2 to the 8, then start out the last digit with 1 minus that. Okay. That way it works out where you add the 1s and you don't add the 0s. Okay. But again, it's not like I'm going to make you do that. And if I do, you can always use a converter. So, yes. Okay. So, yeah, that's all I'll say about binary. But it just makes sense for the computer to store things in binary because of the logic gates and how it's able to either have current going through as a 1 or no current for a 0. And it just makes everything better. The disadvantage is that it does take more space to store numbers like this. So in general, it just takes more space to store everything, but it's a sacrifice that we're willing to do for for the sake of things working out smoothly. So yeah, that's how computers run. It's all on binary, and it's all on bits. So each of these zeros and ones are called bits. And when you hear the term byte, it's because you put 8 of these together, and that makes a byte. So yeah, that's also where the RGB is 255, because you have 255 tones. So it's like an 8-bit RGB, I suppose. Okay, so we're at the 1 hour mark, and that's kind of where I wanted to be. So we have just finished talking overview of computers, binary, the different components of a computer, how they run in the basic sense. And so now we can move on to cooler things. So let's talk about Mac, Linux, and Windows and how they play into the picture of using desktops. So I could split the video, but I am at some point going to start installing VMs, and I will probably pause the video then, because some of those VMs might take a while to install. So I will keep going on this video, and then I'll just end it whenever I need to take a break to actually install stuff, okay? So, or I could cut it and just keep the video really big too. We'll see. That takes effort though for me, because I had to either recompile the video or cut it on YouTube. And so yeah, okay. So Mac, Linux, and Windows, they're all good operating systems. They all have their pros and their cons, and they all require far more time than what I'm willing to spend on to be able to tell you all the good and bad things about them and what they're for and everything. So this is by no means a comprehensive explanation of these. This is just an introduction to them. So let's go ahead and start with the ones that I personally know better. So I started using computers with Windows. I'm a Windows person. Eventually, due to computer science, I started to use Linux. I had never used Linux that I can recall before I was a CS student at one point. As for Macs, I got to use them a little bit in high school, because my high schools had Macs in them, like old school Macs. But I do have a Mac, like I have one back there that I bought, but I don't regularly use them. So I'm obviously biased towards Windows and somewhat Linux. So I wanted to give that as a disclaimer, okay? So the idea here is as follows. So you've seen all the hardware involved. You have your CPU, you have the I/O devices, storage, secondary storage, memory, all these things, right? But who organizes all of these things so you can go on Facebook and watch some cat videos? Like, who actually does all the organization? Well, for that, you need what is known as an operating system. The operating system's job is to be able to take all the resources and coordinate them to be able to have them accessible for programs, software, to be able to use them. So let's talk about like watching a YouTube video, okay? To watch a YouTube video, a lot of components have to go into play. The first thing is you need to have all the hardware. So you need to have like a monitor, some sort of audio speaker or headphones, and you need to have the CPU. And of course you have, oh, by the way, one I/O device I didn't really talk about is the internet, right? That's both in and out device, because you're connecting to other I/O devices around the world, or a server or things like that. So that's a big one too. I forgot to mention that. But yeah, that's an I/O device. So you secondly need that, all those hardware components be up and running, right? So what the operating system's job is going to be is it's going to be able to organize them and say, hey, this is what we have available. We have this monitor. I know how to communicate to the monitor thanks to these little programs called drivers that translate my request to the monitor from the operating system. And those drivers are able to translate requests for all the I/O devices. They're able to communicate and speak the same language as what the OS is working with. And finally, to be able to go to YouTube, you need this web browser, right? You need something like Google Chrome, Microsoft Edge, or Safari, or Firefox, and so on, right? Chromium, whatever browser you're using. That's software. That software doesn't directly go and talk to the monitor or to the internet. it talks to the OS, who's that middleman or person that is going to be able to then work with what's available in your system. Now, why is that middle person important? Because at the end of the day, when you're coding software, you want to be able to code it as quickly and efficiently as possible. You don't know the billion different monitors out there in the world that are possibly going to be used to run your program. You don't want to know. You don't want to know how to communicate to all of them and be able to communicate to the hardware and all of them. That's just crazy. What you do want to know is that if you call a function or you tell the OS like, hey, send this to the monitor, then the OS is the one that can deal with that. And they don't even know that too, because the OS is going to use that driver that the manufacturer of the monitor is going to give to Windows or Mac or Linux. It's going to use that driver information to actually be able to communicate with the instructor. So even Windows doesn't do that, but Windows has that middle person that allows it to communicate, or Mac or Linux. So that's the operating system's job. Beyond that, it's also kind of tasked with organizing information in your system. So there's what is known as a file system or the file directories, and it's where information is actually stored in your computer. Now, I read an article that the newer generation is struggling to understand what a file system is, and that when they download a file from the internet, they don't know where it is, which is kind of scary because, like, you know, previous generations to mine, when I see them using a computer, like, they'll download a file, and then, like, you know, they're like, oh, where did I download that file to? And they start like searching the entire computer because they don't look where they download the file. And to me, I was like, wow, I can't believe they do that. But like maybe like I know how to do that, so I assume like generation after me will know how to do that. But then we're back to that same situation. We're newer generations, so hopefully you're not fitting in that picture, and you actually know when you download a file where you store it. And really, that's the reason for that is at least for the newer generations, it's not their fault necessarily. It's because it just made it so easy. You know, nowadays when you download a file, you don't care too much where you store it because you have a search functionality that works instantly to find that file for you. So do you really need to know where it's stored? It's all virtual in the sense that like you know, if here's a USB drive, right? This USB drive contains all these files in it. Sure, I personally have them in a nicely organized file system. Like folder A is like students, folder B is like I don't know, students from this other class, and so on. Like I have this like amazing file hierarchy that is in here. But at the end of the day, this is just a bunch of silicon. It could be stored in any way in there that is a complete mess, and all the organization is just virtual, right? So is there an argument to be said that if things can be found instantly using other systems, that file organization is needed in the first place? So yeah, there could be an argument made for that. So maybe that's why new generations actually are just beyond that we don't see that as previous generations. Maybe. What I will argue is that the previous generations to mine definitely have no clue what's happening in that sense. That when they download a computer, the file, they're like, what happened? So yeah, so there's that. So I'm not here to try to preach to you that you should do things this way or others. I'm just trying to show you what I've learned in my generation as being the right thing to do, which is to organize things in a nicely nicely organized hierarchy, okay? So that's the other big deal that operating systems are tasked with, is being able to offer you the ability to store files, be able to search for them, be able to organize them how you want, and so on. Be able to organize your programs so they're all working together if needed be, and you can locate and run them, and so on. Yeah, they're that central processing for all the other software that you're using, okay? So again, your browser is a software that is communicating to the OS. The OS is then communicating via drivers to the I/O devices, and that is how you're getting your YouTube, okay? So, all three of these, and other ones that may exist out there, they basically do the same thing to that extent. However, how they do it can vary. For example, how things are stored, how the interactivity between the user and that file system is done, that varies. Mac will have a style. For example, things as simple as how to search and launch a program. So how to search and launch a browser. Windows has things like the had the start bar. I guess now it has the window button now. But it also has the desktop icons that you can click to open things, right? Mac has the launchpad thing at the bottom, but it also has a search functionality that you can do. Linux has kind of like Mac. It has a little launchpad or a taskbar thing to launch things. It has a search feature, right? So they all have their own way of launching programs that is unique to them. But at the end of the day, they do the same thing, which is to launch that program, to save a file, to be able to interact with the drivers, and so on. Mac OS and Linux come to a certain extent from the same sort of parent, so there's Unix-based systems, but there's a lot of differences between them. That sort of division happened a long time ago. But ultimately, that does make them compatible, at least when you're using something like a terminal. Windows is its own thing, but in the recent generations, it has, with something known as the Windows Subsystem Linux, or Windows Sub Linux System, WSL, has sort of brought in some Linux in there. So really, if you know Linux, then you kind of are able to work them both, at least on a terminal level. On just a general usage level, you just have to play with all three to get familiar with all of them to be able to do things. In a separate lecture, I'm going to preach how being a master at Google is really the way to go to be able to learn things such as how to use operating systems, how to do this or that in an operating system. So I'll leave that for another video. So that's all I'll say about the three of them. Obviously, after this, you're no expert, and by any means, right? Like you're still like, oh, what? Well, how do I turn the computer on? Well, there's a button, but like, how do you actually manipulate the computer once it's on? It's tricky. You just have to kind of play around with them, and I struggle myself when things like Windows 11 came out because they changed such trivial things as like the copy and paste icon. Obviously, I just use the shortcuts, but which is kind of bad because in a way, like I don't even know the icons. Like I always have to stop and think like which one's the copy and paste because they made them really weird. Here, I can. I might be able to show you that actually. Oh wait, no. So, for example, right there. So if I click here, this is the copy icon in Windows 11, and this is the rename icon, and this is the cut one. And you don't see the paste one because I don't have anything copied on my clipboard. But see, that's weird. Like okay, this one fair, but the rename one is just like, okay, Windows, why? But oh well, that's what they chose to do. Control C, Control V, life for life. But yeah, okay. So you will know more about operating systems, but first we need to actually have a computer that has these operating systems to use them. Now I could just like go on. I'm running Windows right now and just show you Windows and like give you a tour, but instead I want to show you how to run a VM so you can potentially install any of these and then explore them on your own without breaking your own computer as you're tweaking around. So with that said, let us go ahead and jump into virtual machines, okay? So what is a virtual machine? A virtual machine is going to be a computer inside a computer, like Inception style, but the computer that's inside is not hardware based. It's all running software simulation. So you can think of it like a simulation of a computer inside of your computer. So just like one of the first things you do when you learn to program is to do a calculator, your computer itself is a calculator. So even that is technically a little virtual machine because you're creating a computer within a computer that can do math, right? So that's really all virtual machines are. Is just a simulation of a computer inside of another computer. Why would you want to do this though? Well, such as the scenario here. So suppose I have a Windows machine, but I would like to run a different operating system, such as Linux or Mac. One thing I could do is I could shell out $1,000 to buy a different hard computer and like put it next to me and run Linux in that. And I could do that. I mean, heck, I have the Mac back there, but and then I have a laptop here too. But I could also just go ahead and create this virtual machine, install Windows on it or Mac or Linux, and now I have this fully functional computer that thinks it's a real machine. It's a real machine, but it's really just virtually running. Now, what's the disadvantage of that you can think of? Well, your host machine, which is the machine where the computer is running from, is going to be working hard because it needs to create virtual memory, virtual hard drives, virtual CPU. Everything is virtual, and that takes processing power, space, and everything. It's working to create this. It's a hard task in a way. So of course, if your computer is not up to the task, it can become slow or laggy. The term laggy means it's like choppy in terms of the amount of, if you move your mouse, it's smooth. If it's just like, it means because your graphical unit is trying to refresh, right? So really quickly, monitors, right? How do movies work? Movies are nothing more than just pictures, right? So a picture that is changing fast enough to create the illusion of movement, right? So when you go to a movie theater, at least back in the day when they had film rolls, you had these film rolls and they were running at 24 frames per second, meaning that each frame is a little picture that is being projected into a movie theater, right? And so each picture is like picture 1, picture 2, picture 3, picture 4, picture 5, picture 6, picture 7, picture 8, right? So if you're playing quickly, it looks like I'm waving, but it's really just pictures, right? And the pictures are going at 24 frames per second. And when you record them, you're also recording them at 24 frames per second. So the movement looks fluid and looks real time. If you've ever seen like a really old movie, like those black and white movies, that looks like things are moving quicker than normal or slower, but typically it's quicker, it's because of those variations in the frame rate when they were recording it, because they were hand cranking it or just the way the footage was stored. It changes the speed of it because it's moving faster than when it was recorded. But anyways, monitors use the same technology, or well, the same concept, not technology, clearly different, but the idea of generating the illusion of movement through a quickly changing image. So your monitor's refresh rate, which could be something like 60 hertz, means that it is changing the image at 60 times per second. And so when you're moving your mouse, your monitor has to regenerate the position of your mouse and therefore regenerate the image 60 times per second. That's a high process computing task per se. It takes a lot of math to do that. Particularly if you're moving just your mouse, it's not as bad as if you're playing a video game that's using a lot of processing power to generate 3D virtual environments and so on. So that's a lot of work. And so you have things like a GPU, which allow you to process things in a more efficient way versus a CPU. GPU is a graphical processing unit. It uses floating point notation, floating point versus like arithmetic and so on. But that's beside the point. The main point here is that it takes a lot of power, and sometimes it can't keep up with it. So it can't generate 60 frames per second. So it starts doing like 20 or 10, and that's when things look choppy, just like it would if a movie was playing really slow, and it would start to look kind of glitchy. Okay, so normally the eyes, they see fluid movement above 24 frames. At least when things like movies, that's what the number is. Anything below that, you start to actually see how they're just pictures and not a fluid movement. But that's not to say that the PC master race forums or Reddit is probably like really angry at me saying that because everybody's like, oh, I want higher frame rates, or I want to play Call of Duty at 60 frames, and if it's going at 30 frames, I can see it being laggy. And that is absolutely true. You can definitely see it. Your eyes can detect that. It's just with movies, there's a different sort of illusion because it's being projected, and because you're not as invested in the movement that you can't see it as easily. I think the limit is around 200 plus frames where you stop detecting it, but it varies by person. But definitely you would definitely see something 30 versus 60. Like that is such as clear as night and day. And definitely below 30, you would be having a headache because of how choppy it would be. But anyways, going back to this, not only now are you generating your normal computer's screen, but if you have a virtual machine running with its own sort of image, you have to generate that one as well. So you're working twice as hard. And I would say actually more than twice as hard, because the virtual one, to generate that, you don't actually have the hardware. It's all virtual hardware, which takes its own effort to run. So you're probably working more like 4 times as hard. And that's more of the truth. Although nowadays computers come optimized because they know people do virtualization. So they come optimized with chips like that to make it easier on the computer to run. But it's still by no means on the same level as running something on a host machine. So when you're running a virtual machine, as we are going to be doing, no matter how good the machine is, there is never going to be that 100% efficiency as it would if you were running on a host machine, which again is the one that's running it, the actual hardware. Okay? Yeah, host and virtual. So, how do we run the virtual machine? Well, we, there's things like emulators for video games. Those are also virtual machines. Like you can play like old school Nintendo on the virtual machine. But for things like operating systems and running computers, I'm familiar with two solutions for that. Well, technically three solutions for that. I'll tell you about the one that I won't talk about again. I know things like Docker. So Docker allows you to do some low-level virtualization, and it's very useful for things like when you're trying to run like a really lightweight virtual machine, because you're running a lot of them, so you want it to, by lightweight, I mean it doesn't use as many resources, so you're running it with the bare minimums. Like, if you're running a server, you don't need to have a graphical user interface, which means like new panels you can click on and stuff. It can all be just text-based. So for that, you want to like run the least amount of things you need to be able to put like 20 VMs on the same hardware, right? So for that, things like Docker exist. I do have a video on Docker out there, and I have a paper on Docker as well. But again, I'm not going to talk about that anymore. I want to talk about the ones that we're going to be using, which are things like VirtualBox and VMware. So that's what the screenshots I have here for. So I have VMware, VirtualBox. Now I used to use VirtualBox a lot. It's free, and it got me through a lot of times. And I still have a VirtualBox VM sometimes that I use. But nowadays, I really have moved on to using VMware. Now, VMware does cost money, but I think there's a free version. I actually pay for, well, the university pays for it. It just runs better at least for my usages. That's not to talk bad about VirtualBox. What they do is amazing, and like I said, that was my introduction to virtual machines, and I used them for a long time, and they were great. It's just there were some limitations to it in terms of it just didn't run as smooth, and I could never get copy and paste working between the host and the VM, like drag and drop things, and it's just convenient. So I'm going to be using VMware in this class, but you're more than welcome to use VirtualBox, and just check. And the big disclaimer here: not all computers can run virtual machines. Some of them you actually have to go into the BIOS, which is what this thing pops up when you launch a computer. To change settings on the motherboard. That's another layer below the operating system that I haven't even talked about. But again, this thing goes deep, so I can only talk about so much. But in the BIOS, you may need to turn on virtualization. Go ahead and Google how to turn on virtualization BIOS if you're running into that problem when you're installing a VM. There'll be tons of resources out there, video tutorials, other things that you can do if you're in that scenario. There used to be a situation with the Macs, with the M1 chips, where they didn't have that option. So you just flat out could not run a VM. And it was like, wow, that's a big, like they dropped the ball on that. I believe that has been fixed now, or at least with the newer M1, or they actually fixed it somehow in like previous ones. So that's the thing now. But yeah, so not all computers can run this stuff. So you're gonna have to check up on that. Okay? But yeah, VMware, I would recommend. VirtualBox will get you there too. But if you can do this one, I think there's a free version that you can use. Go ahead and do it. Obviously, I don't want you to have to pay money for these things unless especially when you're learning. I mean, if you use it in your day-to-day life, then sure, you should shell it out or have your work pay it for you. But I would say it's the better one. If you can use it, use it. So, anyways. What I'm going to do with this VirtualBox is I'm going to go ahead and install these operating systems so we can play with them. So I'm going to start by installing them live, and we'll see how we get there, because some of these take a while to install. So this is the part where I might cut the video. We'll see. But I want to show you at least I want to do at least Ubuntu and Kali, which are the Linux ones, because I know that I can get those installed quickly, and while they install, I can talk about something else. The Windows one's probably going to take a while, and I'm not even going to do a Mac one because those take a long time. If you want to do a Mac one, you can check out a video tutorial on those. Uh, it's just kind of painful. But first, let's show. Let me start by showing you how to. Well, yeah, I'll show you that. I was gonna say I was gonna start installing it and then show you, but I'll show you this first. Like if I have to cut the video, I will. Okay. So first of all, download VMware or download VirtualBox, whatever you're using. Again, I'm going to be specifically using VMware for this class. Okay, so let me actually just very quickly go to the VMware website just so you can see what that looks like. So this is VMware, and I have Workstation. I believe that is the name of what I'm running. Yeah, I have Workstation Pro, but I believe the free one is called I think it's like, it starts with an F, I think. Let's see, Fusion. I think that's, yeah, Fusion might be the free one. Or is that the one that's for Mac, maybe? Yeah, okay, so Fusion is the one for Mac. So if you have a Mac and you want to run a VM on it, you get Fusion. What's the Windows one? Maybe Workstation Player. I think that's the free one for Windows. Yeah, so for Windows or Linux, if you're trying to run a VM, regardless of what the VM is actually going to be, so if you're running any kind of operating system you want, Windows, Mac, Linux, even other ones, if you're running those, like the host machine is what you need to download the VMware for. The host machine, if the host machine's operating system is Mac, you download Fusion. If it's Windows or Linux, the host machine, you download Workstation Player. I believe those are the free ones. I think. Again, I have Pro, so yeah. Or you download VirtualBox. Okay. So yeah, and I will talk about so this is that I remember now. I'll talk about the different types of Linux while I install it. That's what I'll talk about. But first, I'm just gonna flat out say we're gonna start by downloading Kali. Okay. So I already downloaded them because I don't want to wait for the downloads to happen. But go to Kali.org or just Google Kali, and you will end up in this website. There is a light and dark mode. Still dark mode. And then from there, you're going to go ahead and click on virtual machines. Now, when you're installing an operating system, you could actually install it. Like here's something I didn't point out that is important to point out. You can have more than one operating system in a machine. You just can't have them both running simultaneously, unless you're running a VM. So, like for example, my machine right here is a Windows machine. I installed Windows in the hard drive, or actually in the SSD in my case. And so when I boot to it, the booting process goes, the computer turns on, it goes into this BIOS I briefly mentioned before. It looks to see which of the drives I have installed, so if the hard drives or SSDs or even USB ports. It looks to see if any of those have a operating system installed. It finds the Windows one, my C drive. It actually uses that to boot Windows up. Okay? You could, at that moment when it boots up in BIOS, select a different drive that it has a different operating system installed, and then run it on your machine, and it would work as long as it's compatible. So that is known as dual booting, and it allows you to install different Windows or Windows on Linux, Windows on Mac, all three of them, and so on. And I've done that in the past. I have a laptop somewhere downstairs, old laptop, that I dual boot. I have Windows and Linux in it. And it's very popular for people to do what's known as a Hackintosh. A Hackintosh is a custom built machine that's running Mac OS in it as well, instead of buying the Mac stuff. Like, you don't have to buy actually from the Apple store a computer to be able to run Mac. You could build your computer, or you could just buy a Windows machine and then install Mac on that. Now, it's tricky, and that doesn't work in all of your hardware out there, because the Mac doesn't like you doing that. They lose money. But you can get it running in a lot of, go online on some forums and find people. They'll tell you which hardware works best. My office neighbor, he has one of those actually. Well, he has one. He tried to build one and it could never get it working. But he had one that definitely worked. So they're known as Hackintosh. So just Google Hackintosh and do that if that's something that interests you. But yeah, the advantages of running a dual boot system with something like Linux and Windows is that if you want to run something on Linux, It's running it on the host level. So you got full efficiency, taking advantage of your computer, as long as it's compatible. What matters if it's compatible or not? The drivers. As long as those drivers are available for Linux, for your monitor, to be able to use your GPU, if you have one, to be able to use things like your mouse and whatnot, which I would say like the mouse and keyboard drivers are available for pretty much everything, and monitors too, but there's some weird edge cases. But yeah, so that's really what's going to limit you when it comes to being able to dual boot or not. And it's all reversible as long as you are careful. When you're setting up a dual boot, you want to make sure you don't overwrite the other operating system by accident. So you would have to put it ideally in a separate partition. So very quickly, I was going to talk about this at some other time, but very quickly, hard drives or solid state drives or whatever it is, there's big blocks of space. You can actually virtually separate them into different partitions, they're called. So the computer sees it as different drives in a way. So like one of them will not touch the other one. So then one partition could be your Windows partition and the other one could be your Linux partition. So useful thing to do. Once we set up the Windows VM, we can go to Device Manager and I can show you that, or I can show you that with the Linux one when we're installing Ubuntu, okay? But that's when we really get to play with the OSs. So if you so far are still not sure on what OS you want and things like that, once we install the OSs and we play with them, you'll get to see that. But yeah, so like I said, let's go ahead and start with Kali, and then I'll talk more about it as things install, because it's gonna take a while to install some of these things, just because we're gonna do it live, and I want to do it live because I want to show you. I mean, heck, we might run into issues, but it'd be kind of good. We get to solve the issues live because you might run into them too. But yeah, I'll talk more about this. Let's just get it going, okay? So go to Kali. In this case, Kali allows you to download something like a bare metal thing. Or virtual machines. You want to download the virtual machine one. This is a nice convenient one because it's going to be so easy to set up. When you click there, it's going to pop up this here, virtual machines. Again, I already downloaded it to save time. And so it gives you the option to download the VirtualBox version or the VMware version. There's also this weeklies. I would just worry about this ones for now. Yeah, just go ahead and hit download here or here. There's also a torrent. If you know how torrents work, you can use that to save them bandwidth. If you don't, that's fine. We'll maybe cover that someday. But yeah, so I downloaded the VMware one, but you can download the VirtualBox one, okay? So when you download that, what it's going to look like, I have it here, is this. So it's just a file that ends with 7Z. That's actually a 7-zip architecture. Or not architecture, extension, which comes from the 7-zip. Like, it's a different format of zipping stuff. So it's compressing data by putting it in a math formula, essentially, to make it smaller at the cost of taking some time to open it because it has to decompress it, okay? But anyways, once you download that, then you're done with that. Let's say you wanted to download Ubuntu, then you would go to ubuntu.com or just Google Ubuntu, and then go to downloads, then click on desktop, and then it'll start downloading it as well. I do have to warn you, these are somewhat, not that large files. So the Kali one is about 2.5 gigabytes. The Ubuntu one is 3.7 gigabytes. So this is what the Ubuntu one looks like. I just downloaded Ubuntu 22. LTS stands for long-term support, by the way, which is the ones you want to typically download, because they are going to be supported for longer. When I mean support, I mean things like security updates, other sort of patches, maintenance and whatnot. It's going to be, so every operating system, okay, so this is realization of the moment of truth here. When you write a piece of code, there is no guarantee, no matter what anybody tells you or tries to sell you, snake oil or whatever, you can never write perfect code. And if they tell you there's some software that can check that code and make it perfect for you, then it's lies. It's impossible to be able to make sure the code is 100% good. And therefore, that's why you all have a job, or will have a job if you go into cybersecurity, because nothing is perfect and there is no real way to find out all these bugs and exploits until they're out there. That's not to say you shouldn't check your code or there shouldn't be some sort of audit. There should be, and you can catch a lot of the issues there, but you can never catch them all. You can't catch them all. And so because of that, because you can't catch them all, there are always going to be some things that need to be fixed, that someone's going to discover down the line. And unfortunately, not all the people that discover them are good people that are going to tell the people that made it, like, hey, I found this issue with your program. You should fix it, because otherwise people can use it to actually access things that they shouldn't and do things they shouldn't. Not all the people that find things are like that. Some people will find it and be like, hey, I just discovered this exploit that I could use to like steal a bunch of money. Why would I tell the developer when I can literally steal $100 million right now? Like, maybe I'll tell them afterwards, but let me get that money first, right? So a lot of people do that. And I'm not here to show you talk about ethics and whatnot, but I'm just saying that's the reality of things. So you have to be careful. And so when you download an operating system, just like any other piece of software, it is bound to eventually have exploits and bugs and things like that. So you want people to be constantly monitoring these things, because A, they can find some of those issues on the line, but also if anybody else finds them, whether they were told by a friendly person or they simply found out because it's already being used to exploit other people, you want them to fix it quickly and to be able to give you that fix. So that costs money. You can't just expect people to do things for free. Although Ubuntu, it's community made, it still takes people's times. And so they can't just support things forever, right? Even things like Ubuntu, where they're doing it out of goodwill and free, they have to at some point be like, okay, we're not going to keep supporting some like 10-year-old operating system that very few people are using just because some people are still using it. We're going to be like, hey, that's it. Like, you're on your own from now on. If there's an exploit, it's on you now. We can't keep supporting it forever. And so that's what this LTS, long-term support, comes from. They promise that until, in this specific case, April 2027, they're going to continually have people making sure that it is safe. And if exploits are found, they're going to try to fix them as quickly as possible, as long as it's until that date. Windows does the same thing. I believe Mac does as well. I'm like 99% sure, but I'm not sure. Whereas with Windows and Linux, I am. They will give you a date and say, this is how long we're going to support it for. And then after that, they'll say, hey, you either upgrade to a new operating system or you YOLO it. So like people that are still running Windows XP, there are some really nasty exploits out there that are just not patched because they don't patch them anymore. And so, or Windows 95 or something. So, you risk essentially bad things happening, getting hacked, if you don't upgrade your system to something that is constantly being monitored and secure. So, Ubuntu, because it's, there's people developing it. There's new versions that you can download that are like betas and whatnot, but they're not promised to be supported for long. So if you want to make sure you get something that is going to be supported at least for a couple of years, 5 years in this case, is going to be the LTS version. Okay, so there's that. And Kali, I assume, has something similar, but yeah. Okay, so that's the Ubuntu. So I now have both of those downloaded. And finally, if I wanted to download the Windows one, well, I'll show you that later. Let's start installing them. I'm really anxious to get this installed. Okay, so I have a bunch of other VMs running, so just ignore those for now. I have a Kali one that's up and running just in case we fail to install the Kali one, and I have Ubuntu ones as well. I don't really have any Windows ones here because I have Windows on my machine. I haven't done this in a while, but I think I remember it. So go ahead and go into your VMware and click on New Virtual Machine. You're going to go to some wizard. We can go to typical for sure. And installer disk. So this is for the ISO. Well, that's for the Ubuntu one, but actually maybe there's another. I think there's an open one. Yeah. Okay. So for the Kali one, because you're already downloading a working virtual machine, I don't think you need to install it that way, if I recall. So actually. Yeah, so actually, so what I want to do first is take your Kali one, the 7-zip file thing, use WinRAR, use 7-zip, use whatever you need to use, and unzip it. So this is what my WinRAR looks like, and I have a folder in there, so I'm just going to make sure that that is going to be unzipped. I'm pretty sure that I have to do that, because if I try to just open it here, it will not work. Let me test it really fast. Yeah, okay. So I'm going to unzip that, Okay, so it's extracting. It's going pretty fast. About 10 seconds it's gonna take. I would show you, but I have to like move this thing. So see, it's extracting it right now. Okay, it has extracted it. Oh, scary things are happening. Okay, we're good. So now I have a folder. Kali Linux 2022 ends with .vmware at the end. I think now I can just launch that and maybe it will work. I think. So I'm going to go hit open there, and then I'm going to locate the folder. So here's the folder. And I open that, and in there is going to be a file called Kali Linux 2022.3 VMware AMD 64. The date might change if you download this at a different date. You hit open on that, and it should be good to go, actually. Like, that's a really nice thing about Kali. Like, it's set up for you already. Basically, what they did is they installed the VM on their own. They set up everything, make it fully working and everything, and then they sort of packaged it up into this little package that you can just share with people and get it really fast. And they kind of mentioned that here. Virtual machine, it says, feeling a little more adventure. Wait, no, that's a different one. Kali Linux VM VirtualBox images are available for those who prefer, whose specific needs require. That's not the one that I. There's a really cool thing. They had like a comment on this that said like, you want an up and running oh, here we go, this one. VMware and VirtualBox pre-built images allowing for a Kali install without altering the host OS, with additional features such as snapshots, bigger images for quick spin up also available, and it has them all basically ready to go. So, and then the password, make sure you see this. The password is Kali because they come in with a password. Okay, so yeah, I just literally opened it and it is right here, and you can see like this is the previous one from 2020 and now 2022. You can go to settings on this, and you can tweak with it if you would like to. I'm just gonna let it all be the same. The only thing is I'm going to make sure that where my disk drive is stored. So the virtual disk, right, where it's storing information, you wanna make sure that's stored somewhere where you want it to be stored because it could take a lot of space. In this case, it is going to store it in this folder, which is where the file was at already. So, you know, that's fine. Just make sure you put that file where you want it to be and don't move it afterwards. So like when you unzip that file, put it where you are going to keep it at, and don't mess with it otherwise. Otherwise, you'll break it. Okay? So I will say that one more time. So when you download the file, you're probably going to download it in My Downloads or something. And so what you want to do with that is you want to move that to the drive that you want it to and put it in the folder you want, and then go ahead and import it like I did here. Okay? So anyways, now it should be just as easy as hitting the play button here, which will start as a VM, and it should work. And voila, that's so cool. Okay, so I just clicked enter, and now it's doing stuff. It might take a while to boot the first time. Just be patient with it. Like I said, this is where I can talk, but as you can see, this one was pretty quickly. This is a pretty nice machine I'm running on right now. So, okay, so then like I said, the password should be Kali. You can change this later, and I recommend you do, but I'm going to keep it the same just because I don't, you know, it's just like the demo one. Okay, so you log in, and again, it might take a little bit here just to log in the first time in your case, and you can see here, I am literally up and running. Like, think about just how awesome that is. Like, it took me longer to download the file, although they had a pretty good server, downloaded pretty quickly, but it took me longer to download the file and like unzip it than it was to like just get it up and running. Like, I have a machine now. Like, just think about how crazy that is. I have a fully functional machine inside of my machine. I want Inception here. And like, if you want to go hardcore, install a VM inside another VM, right? That'd be crazy. Don't do that. But yeah, so now I can do with it. So anyways, I will explore this and mess with it later. But let's go ahead and set up the Ubuntu one next, okay? So Kali is the one I recommend just because, like, you saw that. It's up and running. Like, it's awesome, and I have it ready to go now, and I can do whatever I want. I'll give you the tour, and I'll guide you through all of this in time due. But for now, let's just go ahead and move on to the Ubuntu one. Now, why do I want to show you the Ubuntu one too? Is it going to be the same? You might be able to find an image that's pre-set up like the one that we have here for Kali, but I'm actually going to use the one I downloaded there, which is the ISO. The ISO is what you actually would use to set up a dual boot, because this will be useless for dual boot. Like, you couldn't use this file in a dual boot system. So that's why I want to do that one, because it's going to show you what you would see if you were like dual booting or setup. Okay, so let's move on. So we can, oh, well, I guess some basic operations that you should know here with the VM. Okay, so the first thing is this. The VM is a virtual machine. It's like a virtual world. It's running right now. If you turn off your computer, it like just dies. So two important things that you want to do. First of all, if you're going to stop using your virtual machine, you should turn it off first, and then you can turn off your host device. So there are two ways you can turn off the machine. One of them is you can go to the operating system and turn it off. And again, you don't know Linux yet. But in my case, if I wanted to turn it off, I could go here and click on log out, and then I could click the shutdown button, and that would shut it down. Okay? And after that's shut down, it'll go gray, and then you're good to go. The other way I could do it, which I really shouldn't, but it's good to know in case your system's frozen or something. It's like the old school pull the plug kind of scenario. You can go here, up here where you hit the play button, and you can click where it says power off. And that is the equivalent of you pulling the plug, which is never a good thing for computers. Don't do that. So obviously you wouldn't want to do it here unless you're like hard frozen and you have to just like restart, like force restart it, okay? Now here's where this is where I personally find VMs to be awesome and superior to even like dual booting. There is another thing you can do, and that is called, you can suspend the guest. So what does that mean, to suspend the guest? VMs are super cool because you can freeze the state of a VM. Kind of similar, but not really, to like hibernating in Windows. What you do is you take a snapshot of the current state of the VM, and you freeze that. You save that to your hard drive, your real hard drive, and then you can open that and pick up where you left last time. That is super cool. So like, for example, I have this Ubuntu VM here. And I was using it earlier today, actually, because I was, checking something from a programming assignment. And so I was running it, and when I finished using it, I could have turned it off, but instead I hit that suspend button, like a little pause button. So what it did is it merely just saves the current state, saves all the information from the RAM per se into the hard drive, and then just closes the program. So now, if I want to resume it, all I gotta do is hit the play button, and it'll literally bring it back to how if you had just left it a second ago. Now, it can get glitchy, and once in a while, if you keep doing this for a long time, it might lag it or crash it. But like, I think 99% of the time it works. And that is super, super convenient. I'm coding an assignment for a class, or I'm working on a research project. It's late, or I want to go eat, or I just want to turn the computer off to do something else. I just hit that pause button. It saves all the data, and it closes it, and I can go and do whatever and come back, and it's like right there. So that is super convenient, and I can, because it's a VM, I can still use the computer for other stuff, and whenever it's time to go back to work, I do that. You can do that with Windows too, like hibernating and things like that, but then the computer's like held up to that. You can only bring it back to there. Whereas here, because it's a VM, it's self-contained, I can separate work from fun, right? Like, I want to go play a video game right now. I'll just suspend it, I close it, it's fully closed, out of mind, out of worries, play my game. When I come back to do some work, open it up, restore the session, I'm ready to go. That's super powerful, and I highly encourage you to do that. So, where is my VM? It's like, all right. Keep going. So yeah, so like very quickly, I want to show you that that's the case. Like, I have this terminal here open, and I'm just gonna type like okay. Now I'm gonna show you how to suspend it. So I'm gonna go ahead and hit suspend, and then bam. That's really fast too because I have an SSD. But it could take a while for you. It could take a minute or so because it needs to copy all the contents of the RAM into the hard drive to be able to suspend it. And it even takes a screenshot for you so you can see what's running. So now I could close this program, I could turn the computer off, I could do whatever I want, and it's been saved. So I want to continue it, I open VMware again, I hit play. Again, it's going to take a little bit to restore the information, and then bam, I'm back up and running here, okay? And that's super cool. This disconnected thing, I remember this is an issue. I will look up how to fix it later on. Like, I think, yeah, the internet on the VM doesn't work unless I tweak something in the settings. I think, maybe. Oh no, the internet works here. Google.com. That used to be an issue. I remember that used to be an issue with the older 2020 VM. There was an issue with the internet that you had to like tweak around. But this VM seems to be running with the V internet, so super awesome. It's really working fine. So yeah, so you can see that's an example of me restoring it. Okay. The other thing I could have done is I could really shut it down, and then it's properly shut down. Voila. Again, I don't do that anymore. Why do that? I can just save the state and literally pick up where I left off. Like all my windows are in the right spot. Like you can see that in this one. Like I have literally all these windows nicely organized so I can keep coding and working on this research right the way I like it. All you have to do is hit play, work as long as I want. When I want to take a break, pause it. When I want to come back, I'm right there and then. Highly, highly encourage you to do that. Okay? But anyways, moving on, let's go ahead and set up the Ubuntu one, okay? So the Ubuntu one will be more tricky. So that one, we're actually gonna go to new virtual machine instead of the open. And then we're gonna go through the actual UI here. So when I hit browse, I'm going to locate the VM I downloaded, which I put in this Ubuntu VM4. Here's the ISO, hit open. And then the VMware is really cool, because it already has these like presettings to make it easy to install, which I'm going to do. Otherwise, you would have to manually set up a couple of things. So here it detected that. It says Ubuntu detected that operating will use easy install. And so I'm going to do that. But if not, then what this does is it saves you a bunch of hitting next. Like pick the language, pick the country, pick your username and things like that. Actually, username will ask me. But yeah, so I will do that. I will hit next. Personalized Linux. So for this, I'm just going to, you can leave this blank for the full name. I'm just gonna put something like my YouTube thing, I guess. So actually, no, I'm gonna call this Linux test. And my username, I want to make it easy for me to remember right now. So I'm going to do Ubuntu, and the password I'm going to say Ubuntu 2. So like the same as the username, okay? Put a safe password here, okay? I'm just doing that so that I can use it for demo. And I'm gonna write that down here on the side, because otherwise I will forget. That'll be literally a meme. Okay, all right, the virtual machine name, I'm gonna call Ubuntu 64 VM4, it's just for me to keep track. And then here is important. Change the location where you wanna save it to whatever you want to do for like the location, okay? I have a bunch of drives, so I actually have to keep things organized. So I'm gonna put that in that folder I made. I'm probably gonna delete this VM after I make it. Just after I make it, I'll show you all, since I have a bunch of Ubuntu ones. But yeah, so here we go, Ubuntu VM4. So that's the location of it. And hit next. As you can see, by the way, this is F drive. It's gonna ask you how much hard drive space you want. So basically, you need to allocate some space for the VM to be able to store data. Whereas the one that we downloaded already had that predefined. Here it's asking you like how much you want. You can go with the defaults. I'm gonna amp that up to 30, just to be safe. Whereas whether you want single or multiple files, singles will be better for a better performing machine. Multiples will be slower slightly, but it allows you to copy them between computers, which is kind of like the other method. So actually, I'll keep it with split. Why not? Okay, and then everything else should be pre-configured already. So just hit finish. Otherwise, it might ask you like how much RAM you want and things like that in VirtualBox, or if you didn't do the easy mode. But yeah, so now this easy mode is going to do things where I don't even have to click anything. It's going to click things itself to actually set it up. So this is the part where I'll probably talk about something else while it does it. But let's just look at it for a minute and just see how cool it is, right? Actually, it's like bring it up a little so you can see it fully. There we go. So yeah, so it'll handle like all the like menus that you'll see initially when you boot it, which is like, hey, welcome. How would you like to split the storage and all that? So yeah, so here it's booting Ubuntu, and it's going to be like, welcome to Ubuntu. Would you like to install Ubuntu in your machine? And there's music playing actually. That's new. That's new for Ubuntu. So it's asking you like what the keyboard layout is and whatnot. I think it'll do that automatically. Or is it asking me to click it? I guess I'll click it. All right. Hit continue. Normal installation. Don't want to download updates while installing. Nah, sure, I'll do that. Nah. I mean, I'm not going to keep the machines, that's why. You want to do that, though. You definitely want to do that. I just that I'm going to, like, delete it afterwards, probably, because I have other ones. But sure, why not? Oh, no. Maybe I shouldn't have done that, because then I might slow down the installation because it's doing that. For this is where you need to be careful if you're doing dual booting. It's asking me if I want to erase the current disk where I'm going to install Ubuntu. If you're using dual booting, you don't want to do that because you might have something else in that disk, unless you're using a different disk. If you are, you're going to make sure you're deleting the right disk. In this case, it's a virtual disk, so you can erase it because it's virtual and there's nothing in it. We just created it exclusively for this. So now it's asking you to confirm how it's making the partition. So remember the partition thing I was talking about, how you can split this into multiple components? That's what's doing it here. Linux needs different partitions for different things, such as storing files for the configuration or like the actual OS files and whatnot. So that's just asking you to confirm that. You can get technical and choose different settings for this, but if it's your first time, don't mess with it. I feel like I broke the easy install because it's asking me all these questions that I normally would not ask me. Like this should automatically autocomplete. Press Control Alt to release the mouse cursor. Control Alt. There we go. Nope. Yeah, I think I broke the auto install because of something I clicked, but it's fine. I'll just do it again. Probably because I clicked away from it. Ubuntu. Weak password. I know it's weak, but it's not. Log in automatically. But yeah, okay. So yeah, that's installing, and as you can see, this is not as easy as the Kali one. Well, not easy, not as nice, but you do have more customizability, and it's probably going to end up working better in your system in the long term, because there can be some buggy things when you're like, for example, I've in the past moved VM machines from different hosts, and sometimes they work off the bat, but sometimes they don't. Like especially VirtualBox actually. Like I remember one time, I had an office in the computer lab at UNLV, and like my first semester that I was teaching, and so eventually I was able to move to my own office, right? So like moving meant taking the virtual machines with me, and so because I didn't take the actual hardware, so I just copied the VirtualBox image, and like it worked, but like it was so slow, like horribly slow, and it was painful. I eventually just made a new one and deleted that one because it just became unusable. So that's an example of where the VM does not transfer well. Again, another reason that I like VMware, because I didn't really run into those issues. Like when I built this machine, before I was using a machine back there, and all my VMs worked. I transferred them and they just worked. They had no lag issues, no whatnot. In fact, some of these that I have here are actually from the old machine. So yeah, not to try to sell you on VMware, but it just worked better. So yeah. Anyways, This is almost finished copying files, or at least that's what the description says. So while that's going on, let me show you where you're going to download Windows from. And that's the one that I probably won't be able to show you live install because it's going to probably take a while because Windows. But who knows, maybe it'll work because of the prepackaged stuff. Maybe they'll work. Fingers crossed. I haven't done the Windows one in a while. But yeah, if you want to download the Windows one, just go ahead and Google like Windows 11 or Windows 10 VM machine. And then you get to this website, which is called, here, let me scroll down so you can see it, developer.microsoft.com. Always verify that this is coming from a legitimate source of HTTP, like the HTTP website is correct, and it's HTTPS if it's encrypted, because you don't want to download a virus, things like that. Basic security 101. But yeah, so from there, you can choose VirtualBox or VMware. As you can see, this is a much bigger file, but the servers were nice. It took a couple of minutes to download. 20 gigabytes. And I have not run this specific one. I actually never used the Windows 11 VM. I only play with Windows 10, so be interesting. I mean, I have Windows 11, but who knows? Hopefully that works. That'll be fun. But yeah, so you download that, and once you download it, same stuff as this. This is still doing stuff. I could probably install both VMs parallel to each other. Could be risky, but this is the time when I want to take to talk to you about file hierarchy and how it works. Just a little basics of that. Although I think most of you know it, I want to just go over it. But yeah, so just so you know, this is what I got when I downloaded the Windows file, 20 gigabyte, and it's a zip file. So it might be a good idea to unzip it actually. So we'll do that actually as well, because that could take a while. Yeah, it's extracting. This is about 3 minutes. So I'm glad I started that. So yeah, so make sure you extract. This one's just .zip, so you're not going to need like a 7-zip or WinRAR, which you will for the Kali one. In fact, very quickly, let me actually show you that. Let me show you what 7.6 looks like. So this is 7-zip, which you can use to. It's like an alternative to using like the built-in like zip file thing in Windows or Mac or Linux or whatever. But it has more formats, so I encourage you to use this. The other one is WinRAR, but WinRAR is not free, but it's freeware in the sense that you can use the trial version forever. But it'll tell you should pay after 30 days, and it's an ethical question, like if you don't pay, are you stealing kind of thing. So if you don't want to feel guilty about any of that, you can use 7-zip. Okay? If not, let me just show you what the WinRAR page looks like. Here you go, WinRAR. I mean, those guys work on that. I would not feel bad paying them for that. So pay them. But yeah, okay. So where's this? How's this number on? It's still installing. Okay, so yeah, so I think the no, it's not done yet. It's 1 minute 45 seconds for the unzipping of the Windows one. So yeah, let's talk about file hierarchy while that happens. Okay. So first of all, a couple of words that I should spell out for you in case you don't know. Kali, Ubuntu. Windows you can spell because it's just like a window. And then Mac OS you saw it, but here it is, Mac OS. Okay. I will talk about the different types of Linux, but just very quickly, like I really want to get into this file hierarchy stuff. So this is how normally computers store information, at least when it comes to all the 3 big ones that I said there. And so it's all in folders, the concept of folders, okay? So normally each drive, so you have a drive, and that stands for a hard drive, HDD, hard drive disk, or SSD, solid state drive. And so you don't really see the difference when you're looking at a computer. Like you just see them both the same as a drive letter. So the drive letters will just go like A, B, C, D, E, F, whatever. In Windows and things like that, typically you have C as your main hard drive where you're storing the operating system. So this is your system drive. And then the other ones are additional for files and things like that. When it comes to Linux, you saw a little bit there with the partitions and whatnot. It works on a partition level. But ultimately, you'll get to explore that more once I have the Ubuntu one running and the Kali one and whatnot, okay? So moving on from that, once you're in a drive, you can create these folders. Okay, so like if you're looking at a user interface, whether it's Linux, Mac, or Windows, you typically have a little window here, and you have things like the close, the minimize, and so on. So in fact, you have this, and then you have the line. So like this is used to minimize, this is used to maximize, make full screen, and this is used to close, right? Okay, so in there, you will typically see little vanilla looking folders. Or actually, well, I guess they're blue now in Mac, because Mac wanted to be different. So these folders are how you store the information. So within the drive, what you're trying to do, again, the drive is just another mess. It's whether it's a platter or it's a USB drive or SSD, that is all over the place. You have some control of how information gets stored, because you can do things like defragmenting for a hard drive. But I mean, at the end of the day, it's all chaos. So all of this organization is strictly for your benefit, for that virtual organization. Okay, so you have to separate real from virtual in a way. It's not like in your office where you like separate things nice and neatly. Like, no, this is all happening behind the scenes. But in reality, it's all like, it's just all blah. You know, it's like for example, me. Sometimes I'll have a bunch of papers and they look messy to other people, but like I have a very clear definition of how they're organized and I know exactly what I'm doing. But some people might be like, hey, that's just a stack of papers. I'm like, no, I know exactly what I'm doing. That's kind of how the folder structures work in Windows and Mac and Linux work. It might look messy if you just look at the actual physical hardware, but it's organized in a virtual fashion, okay? So the way that the hierarchy of these folders work is like a tree. In fact, it's a tree. In the sense that you start out by choosing a drive. So this is like, okay, I'm going to start looking at this hard drive or this SSD. And within that drive, you create these folders, right? So let's call this folder like CS202, CSEC 700, or better yet, maybe we have a folder called school, and one called work, and one called programs, and so on, right? In that folder, you have other folders. So for example, I actually think that these two folders should really go inside of the school folder, because that's really more of like a good hierarchy. So maybe I have the school folder here, and I have a work, and I have this programs folder, okay? So inside of that school folder, if I open that folder, so let's say this is school, I have subfolders such as this cybersecurity folder, or this CS202 folder, or this data analytics folder I could also have. I could also be more organized and say, instead of having a CS202 folder, I have a folder called CS. And in there, I have a folder called 202 for class 202, 302, 135, and so on. So that organization of your folders is called a file hierarchy. And it's how you want to organize your data so that you can find it easily. So if I want to find out let's say I'm working on an assignment for my 202 class. I want to find out where that's stored. Well, I start by going to the school folder. I'll go to the CS, I go to 202, and in there I probably have folders numbered like 1, 2, 3, 4, 5, and they represent the assignment number. And of course, I have to make that assumption. I guess I could call that AST1, AST2. But and so on. So that's just a basic idea of how to store things. I know this is hopefully like, oh wow, I can't believe you're going this basic. But you'd be surprised. Some people don't know this, and I want to make sure I cover everybody here. Like, no person left behind. But anyways, I would like to interrupt your broadcast to show you that installation complete on Ubuntu. It says you need to restart in order to use the new installation. So let's go ahead and restart now. So click restart now. And it's doing it. Oh, by the way, so like right now I lost my mouse. So if you ever lose your mouse, you do that Control-Alt thing to recover your mouse, okay? Because it's stuck inside the VM. For VirtualBox, similar command. So now it's restarting, and also I would like to inform you all that the unzipping of the Windows one also finished. So there's that. Okay, so now I'm going to resize this. And it's, you know, you skip this. It's like some final setup thing. Nah. I don't want to send anything right now. Don't turn on location services. You're ready to go, and I am really ready to go. So there you go. I have Windows, or sorry, I have Linux up and running. So here you go. Now we have Ubuntu, actually, not just Linux running. Okay. So yeah, let's look at that file hierarchy on Linux. So you can see all these folders, and in them there's nothing because I mean I just installed it. So probably all these are empty. But if I want to go to the most bare folder, I can go to other locations, click on computer, and so this is like if I had other drives, they would show up here probably. And so this is the basics. So like my root directory, that's usually all the important stuff is kept per se. On the home directory is usually where all the user stuff. If you get something like this for update, I recommend you do update it. In my case though, I'm not going to update it because I can do that later. The home directory is where all the user files are stored. So if I go there, you'll see Ubuntu, but in your case, it might say the name of the account you have. So remember, I made my username Ubuntu, my password Ubuntu. That's why it says Ubuntu there. But like, it would say, I don't know, Timmy or whatever, Timmy's iPad, if it was that one that you were running. So yeah, and then you can see there all the folders there are the same that were here. So that's the hierarchy of that. And I can make a new folder here too. Although the new Ubuntu removed for some reason the thing. Oh wait, no, I do have new folder. You just can't make a new text file. That's right. But yeah, if I can make a new folder, I can say videos, lecture videos. And so I have a folder there. If I want to know what the hierarchy of this folder is, I can go to the properties tab. And you can see here it's in the home folder, inside of the Ubuntu folder, inside of the videos folder. It's called lecture videos, and it talks about permissions and other things. We'll talk about that at some point. It tells you when it was created and then when it was modified. I can put in their files now. So if I guess I should show you this. I always forgot to do it myself, but I want to show you how to do it. Because it's like, for me, it's such a basic thing to be able to right click and create a new text file. So I always have to Google it. Because they, for some reason, they decided to remove that. And there's a thing you can do in the UI for that. Okay. I forgot how to do it and I can't. Oh, yeah, that's right, templates, yeah. So go to templates here and then just add a new text file there. Now, you might have to open the terminal and type in touch and then write in like new document or something. New document. I'll explain the terminal when the time comes. But if you do that, then you have this new document here. Now, what the effect of that is if I go back to, what was it, videos, lectures, I can right click here, new document. So I can make a new text file. The reason why I wanted to make a text file is because I can just write some stuff in it. Like, hello world. And so now I can right click on this and you can see the hierarchy of this. Okay, so yeah. Anyways, this is Ubuntu. Okay, and I will explain the, well, let's explain it now actually. Well, I'm anxious to get the Windows install going because I have a feeling that might take a bit. So I will explain the differences between the different Linux, but let's just skip that for now and let's just try to get the Windows one going, okay? So let's, I don't really need to save the state for this, so let's just power off. So click power off, power off, power off. Or you can suspend the state. By the way, if you just close VMware by hitting the X up here, and any VM is running, it'll automatically put it in the suspend state for you, which is super convenient. That's actually what I do. I never hit the pause button here. It just, I'm like, yeah, close it. Yeah, no, it'll do its magic. You're good to go. But yeah, the difference between that is that you will see a screenshot when it's suspended versus just like a black screen. Okay? But yeah, okay, so let's try to get the Windows one, because I'm nervous about that one. So, okay, so Windows, OBF, oh gosh. All right. And hit open. Provide the name and the local storage path for this. Browse. Okay, so let me just, again, put this in a folder that I want. Hierarchy right here, right? Now you know. Let me actually make a folder. I'm super like picky about this stuff. So I'm going to create a folder, hold VM files here. And then I'm going to use that and select that here, like, just so you can see what I'm doing. I am selecting it right here. Hit OK. I'm going to call this, I'll leave that name, eval, whatever, sure. And then hit import. And yeah, it's going to hopefully import. It's going faster than I thought. That bar is moving better than expected. But yeah, okay, we'll let that run. In the meantime, I will explain to you the different types of Linux. So, with Windows, let's talk about all OSs actually. So with Windows, we have different Windowses, but typically there's only one real active one. So like, for example, right now, when I see this video, most computers are using Windows 10, but Windows 11 is available, so we're starting to kind of phase into that. And that's why I got Windows 11, because I wanted to make sure I don't become old and start using just like the really old one, right? You gotta keep innovating. So that's where that is. Mac is a little more strict with that. They usually kind of go with one version and then they just like jump everybody, kind of like you just jump everybody. But they also kind of keep a versioning system like that, and you typically just stay in the latest one, as long as your machine can handle it. Linux is different than that, because Linux is more of is not necessarily one operating system. It is a group of operating systems that are running under that same sort of basic system. And so you have things like Kali and Ubuntu that are both running Linux, but they are their own flavor of it. So because the Linux is open source, there's different groups of people, a lot of them doing this stuff for free, that that basically make their own version of Linux. You know, like for example, Raspberry Pis, a Raspberry Pi somewhere back there, and that has its own version of Linux that's called Raspbian. But there's also like Ubuntu and all these other Linux versions that can run on that. And so there's Linux made specifically for some hardwares, like those OS, like that one needs a special OS for the Raspberry Pi. But even for desktops, there's a lot of them. There's Red Hat, there's CentOS, Ubuntu, Kali, and so on. I could probably find a list for you on Wikipedia. That would be my best guess. So if I go and say all Linux variants, well, that's probably going to be massive. Maybe there's a cool picture. Oh gosh, this is much. This is hardcore. But maybe I'll show you this picture, and I'll show you this picture. This looks like a subway train map. But it does show you kind of a good idea of just how ridiculously big things are. By the way, the Windows thing finished. That was pretty fast, actually. But let me finish talking about this. So this is a timeline of all the Linux out there. And as you can see, there's a lot of them. I'm still going. So in the beginning, there was nothing. And from there, the Linux people said, let there be Debian. So Debian is a group of different Linux systems that include some of the popular ones that are going to be, well, a lot of these are, there's so many. Raspbian, that's the Raspberry Pi one. It's up here. I'm looking for Ubuntu. Kubuntu is here. Ubuntu, here we go. There's Ubuntu. So like, as you can see, Ubuntu came around 2004. And from there, even from Ubuntu, there's been like variations of Ubuntu itself. So you can think of like Ubuntu's parent is going to be Debian. So that was like the first of that set. And from there, people developed a bunch of different ones. One of the most popular ones being Ubuntu. So popular that people in Ubuntu were like, hey, we like Ubuntu, but I wish you could do this in Ubuntu. So then they made their own version of that. And those people were like, oh, this is cool, but I wish I had this and this. So I made my own version of that. So that's how you ended up with all these crazy amounts of them. For example, there's Ubuntu. Ubuntu is a version of Ubuntu that's like more bare bones to use on like lower tier computers. not lower tier, but like computers that are as many specs. So like, you know, like for example, like if your computer's really old or you're trying to run a Raspberry Pi or something low powered, then you want to use something that uses a lot of power, so you use Ubuntu. There's Linux Mint. I've heard of that one at least. There's Lindos. I assume that's some weird version of Debian, of Linux, that they try to make look like Windows. I know there's a bunch of those like that. There's ones that make it look like Mac. They're all over the place, and they're all cool. They all have their own variants. I mean, the Russian and the North Korean OSs, I believe they're Linux based, so they're probably somewhere in this list. I will try to make this available to you all. I actually, interestingly enough, this came from a link from a VMware blog. That's pretty neat. So I will make this available to you if I remember to. If not, then this is the link. Blogs.vmware open source 1027, choosing a Linux distribution. Okay, and you can find it if you just Google like all Linux variants, and you'll find this big chart. Yeah, I don't think they made a chart either. They probably just pulled it from another place. But yeah, so another big one that I want to point out is Red Hat. So Red Hat is kind of like the paid version of Linux, because it's more like for industry and things like that. So that's one that you probably run into. You have Red Hat Enterprise and things like that come from that. Oracle Enterprise, these are all like, this is like the money side of Linux that you'll see in industry, and they have to be more careful about how things are handled, because you don't want some mischievous person changing the open source and inserting bad things. So there's that. Some of these are like, they just lived and died kind of thing. They didn't really become big. Like I said, the ones that I'm personally familiar with, some like the Raspbian maybe, Ubuntu, Kali, CentOS, because it was used at UNLV for a while. CentOS is kind of dying though. I believe the people from Oracle, or somebody bought them. CentOS, who bought them? CentOS bought by Red Hat. Red Hat, yeah. So Red Hat was bought out, and again, Red Hat is like the money side of Linux, and they kind of, well, partially is because some of the people that are in Red Hat originally worked on CentOS, and they were like, hey, we're gonna buy it, baby. But also they kind of slowly killed it in a way, which is scary. Like they started using it as a test branch of Red Hat. So yeah, I don't know. The reason we had it is because it was like Red Hat free, basically, and so it was good for UNLV. But yeah, it's gone now. Slackware, what's that? I'm really familiar with that, to be honest with you. Not really familiar with Slackware. And somewhere in here is probably Kali, but because it's, oh wow, and they're all clickable, so you can click on them to find out. So could I Control F Kali in here? Hey, there's Kali. Hello, Kali. So where did that come from? Debian, as you can see. And it has no branches off of that. Hey, there's Raspberry Pi OS from Raspbian. That's why I think they renamed it. That's why it just pops up there. But yeah, I welcome you to play around with this and take a look. Obviously, we're going to be sticking to Kali and Ubuntu for this. I personally like Ubuntu for my regular day-to-day life. But yeah, there's a lot of them. If I was to pull something like this for, you know what I want to keep? I'm going to try to save on a different window the the source of this, so that I can hopefully post it on the YouTube description. So I'm going to just put that over here. Okay. Here's a picture of some of the icons. Just out of curiosity, so Linux is this is the typical Linux thing, is a little penguin looking thing. Ubuntu, Fedora. Oh yeah, Fedora is a popular one too. I forgot about Fedora. Let's see which other ones I recognize. Well, Debian. CentOS, there's CentOS I was talking about. Red Hat. I'm surprised Kali's not in here actually. It's kind of sad. Maybe it is and I'm not seeing it. Maybe this is Kali. I don't remember the icon for Kali actually. But yeah. Okay. So for Windows, if I wanted to show you like the Windows, maybe if I look at like Windows timeline, maybe that will show me. It's not really what I wanted. All Windows logos. Maybe if I look up all Windows logos. Yeah, this is neat. So here's what that looks like for Windows, at least until 8. So here we have 95. So that was like the first like proper OS. Before that, like 3.1 was like, and all the stuff before that was like more just a terminal. This is one of those like what we think of on the OS as today is like Windows 95. That's like the granddaddy of that. Then you have like, this is skipping a bunch of them because this had 98 as well. There's 98 second edition. Windows XP was a huge game changer as well. It also modernized what you typically think of Windows as today, and it stayed for a long time. It was like the big thing. Vista was like so-so. I think it was like the beta version of Windows 7, which was a big one that was very popular. And then Windows 8 was also kind of iffy, it's like touch and whatnot. Then you have Windows 10, and now you have Windows 11. So that's been the evolution of Windows as well. And like I said, I'm not as familiar with Mac, but I could probably find some sort of picture similar to that. So I don't know. I mean, Google tells me this. So I've never seen any of these, except I know Catalina, Mojave, High Sierra. I know these ones, and then this one too. Oh yeah, I would say from here on, I recognize these names, but it's missing a lot of the Mac stuff there. Like, where's like the old school Mac stuff? I don't know. But yeah, I mean, Mac's Mac. They try to be their own thing. Obviously, they succeeded a lot nowadays to be like the hip one. But you can definitely read the story of Mac and Windows and all of that. You know, or check out. I think I might talk about it in 2019 at some point. Probably not that detailed. You just have to Google. Just Google like history of Apple and Macintosh, which is what Mac stands for. But they kind of dropped it at some point. Okay, so we're 2.5 hours. We're almost there. Let us try booting the Windows one and see what happens. And I think that's what we'll call it. And then next time we'll talk about the terminal and explore the OSs. Okay, so it finished running, so now I'm going to hit play and hopefully it doesn't explode. So, hit play. Oh, I see the Windows logo. It's probably going to try to go to some initial setup. That's going to take a while, maybe. Or no, actually no, because it's a pre-made image. So maybe it'll just take me up to Windows. Maybe. I hope. I don't know how this Windows 11 version was set up. We'll see what happens. Yeah. Very interesting thing. But I think I've covered it pretty much everything I was hoping to cover for the first 2 steps. Pretty much from here, what I want to do in the next video is walk you through just the basics of Windows, the basics of Linux, and then lead that into using the terminal. Now, why is the terminal so popular? Because the terminal is the way things used to work before you had a graphical user interface. And so really like, now we kind of have it nice, but you don't always have it nice because sometimes you're connecting to a server. And a server is trying to, again, be as efficient as possible, so it doesn't need to have all the nooks and crannies and pretty pictures. So it's all text-based. And so that's why servers are still popular today and used a lot. And you would not see some user interface for that. Okay, as you can see, we're getting the stuff you get when you just first launch Windows in a recently installed machine. Oh no, it might take a few minutes. Does that mean I have to teach for a few more minutes? I'm kind of tired. I could just cut the video and see what happens. We'll see. Maybe if it doesn't take too long, I'll let it go. Because I was really aiming for that 2 hours and a half long video, which we're about to hit in a minute. It would all would have worked out if Windows didn't decide to take so long. I should have launched it earlier. That was my mistake. Is there anything? I hope it's a lot of material to really cram into a video. We went from talking about like von Neumann and like what makes a hardware to like running a virtual machine. That's like a lot to go through, really. But definitely important stuff that I want to make sure we're all on the same page. So you might have known all of the content in this video. That's okay. But some people might not. And that's who this video is made for. So there's that. Okay. So if it takes too long, I will cut it, and then I will do like a addendum video. I might just chop this part of the video off on YouTube once I upload it, and I'll just like concatenate it. But it says almost there, so it's like teasing me. It's like it's almost there. Oh yes, I don't have to cut the video, because cutting a video on YouTube takes like a day for it to process. And if I cut it manually, I have to then re-encode the video, which will make my GPU run at max speed for a while. So yeah. So anyways, oof. Okay. Yes. Yes, we have Windows. It works. Thank you. Thanks the maker, as C3P would say. Let's take a second to honor our fallen heroes on today. 21 years ago. But yes. Okay. And we have Windows. So as you can see, installing Windows is not bad. It's just a bit of waiting that we had to go through. But it was almost like the Kali in the sense that it has the VM pre-set up. The only one we properly installed from quote-unquote scratch was the Ubuntu one. This one, as you saw, and the Kali one is just really downloading that big massive file and just letting it do its magic. Unzipping it and doing it. And so yeah, so now we have Windows, and we'll be able to explore Windows. So here's that launch bar very quickly, just so you can see the hierarchy. If you go to computer, or this PC, it used to be called computer, you can see you have a C drive, and you can see it has some space in it, and you can see the directories and so on, and each one goes in and whatnot. And we'll play with all of this. I actually will keep this VM here, and the Ubuntu one I might throw away. But the this one I will keep because I don't have a Windows one. This is the first Windows one I have. I'm so happy about this like working, because now we can actually play with it. And one important thing you always want to do with VMs, but I don't, but you might, is you can save a snapshot of the machines so that if you break the machine at some point, you can easily restore it. There's a lot of ways to do that. I believe if you go to, there's some settings you can go around, but frankly, the easiest way to do it is just to go to your directory where you have the machine and just back that up, you know, like so. This one is all the VM machines, so just back that up. And that's kind of what they're doing when they're sharing these VMs. They're just backing them up that way. The only issue you might run into with that is the question that I asked about making one big file for the hard drive or smaller files. If it's one big file, that will not work as easily. If it's smaller files, it will work. But yeah, so here we go. Today we have installed Kali, Ubuntu, and VM. So we're ready to go to start playing around. I welcome you to try doing this for Mac. It's a little trickier because you got to get the ISO. So it'll be a lot like the Ubuntu install. You have to get the ISO from the internet, from official sources. Be careful. And then download that and then go through the process. You have to go through all the setup, probably make an Apple account if you don't have one, and you go all of that, and then you do it. I may end up doing it at some point. If I do, maybe I'll set screen recording on and like go through the process, and then maybe like compile a short video of how to install that. But frankly, there's so many videos out there that you can probably find them. So maybe I'll just set it up on behind the scenes, or maybe I'll just use my Mac and show you from there if I ever need to. But really, it's all leading to using Linux. So that's why it's not as important. Even Windows has this Linux version called WSL. Oh yeah, I want to test that. I want to see if that runs. Oh, what is it selling? Yeah, but I'm assuming it'll run once we get it running, because that was one of the big advertised things for this VM was like, hey, it has WSL ready to go. Just to show you what it looks like when it's running, at least when it's running the terminal version. There's a UI version, but I haven't gotten it working yet. Let me clear that out so you can't see IP addresses. So once it's running, oh wait, it's working here. So username, I'm gonna use Ubuntu for the username. Password Ubuntu. Retype password Ubuntu. Okay, so there's that. Okay, so you can see that it is working indeed. We have the so we have a Linux terminal in Windows if we wanted to. So that's why learning Linux now is just like the shortcut. You don't need to learn too much command prompt. But yeah, okay. Well, that's it. It's a lot of video, but we did a lot today. So thank you all for watching, and I hope that this video was helpful. And I'll catch you on the next one. Take care. Have a great day.